Yeah, you can go ahead and put the screen up. I'm not mirroring, so that's happening.
Are we streaming now?
Yes.
I can go back to presenter testing.
Should both screens have the same thing?
Oh, is this my coffee, Chris?
Yes. Okay, begin. Great. Hello. We are here for the miniKanren workshop. I'm very happy to have you. I'm Chris Martins. This is my co-host Will Bird, who has been the guide throughout all of this process for me very much. But great. So I wanted to just briefly preview for you the events of the day. Because we're doing things a little bit perhaps unusually. You might be kind of used to a workshop format that's more stuff that deals with talks, and we have some wonderful talks for you today, but we also have the opportunity to provide a little bit of other programming that we hope will maybe bring some new people into the wonderful world of relational programming through a tutorial, and then I also have a challenge problem for you. So for those of you trying to get your bearings with miniKanren or who are already seasoned experts and want to just try out something fun, I'm gonna show you something at the end of this session for you to try throughout the day. And then there will be an opportunity at the end of the day for you to demo whatever you came up with, and or just an open mic session for you to share whatever you've been working on. That's kind of like at a high level what we're doing. So just to scroll through that a little bit more, we've got Will's tutorial, my programming challenge, then we'll have a break. We'll have 2 talk sessions on either side of lunch. And in these talk sessions, we're actually going to allocate for each talk a pretty generous discussion period. We're going to follow a format that I got from Sri Ram Krishnamurthy, he got from Kathy Fissler. And the format for these discussions, it's going to start with basically, at least as long as there's enough people here to warrant this, we're going to have a small group discussion. So after the speaker concludes their talk, we'll have everybody like at a table, let's say, just chat with each other about what you got from the talk, any questions you had, like try to resolve any misconceptions. Get all those questions out of the way that if you came up to the mic and asked it, you might be embarrassed because it was something obvious that you missed, right? Like anything you can kind of help resolve during that discussion period. And then after that, there will be an opportunity for actual Q&A with the speaker. And then finally, I think we're going to try to give you some time to write out your thoughts on on a piece of paper as written feedback to the presenter to help them with their next directions of work on that project, and we'll collect those from you and hand them to the speaker after the fact. So does that kind of general idea will make sense? We'll also walk you through it when we get there, but this is going to be a little bit of an unusual, not a standard Q&A kind of thing. Hopefully give you a little bit of a chance to get to know each other as well. Great. Yeah, so we're going to do 2 talks with 2 discussion periods, then lunch. 2 talks, 2 discussion periods right after lunch. We'll have another break, and then we'll finally have our afternoon keynote from Jason at the end. So I think that's a good.
And the demos.
Yeah, and then the demos of the program. So hopefully during the breaks or whenever you're if you step out for a moment, you can hack a little bit in your relational programming language of choice on that problem.
And I was just going to say 2 other things. So, we have the talks, 30 minutes, and hopefully the speakers probably take about 22 minutes, and then we'll have some, discussion and Q&A. But with these blocks of time after the talks, so 15 minutes, our thinking was, because this is a fairly small community and a fairly small workshop, it's a shame to have people just sit through talks or panel discussions or tutorials and not get to meet each other and talk and maybe even do a little hacking on miniKanren or some other language. You know, part of it was with the challenge Chris is going to give. You can use any language you want. So, you know, part of that idea is not just to give feedback to the speakers, but also to get to know each other. And I would hope, what my goal for every conference and workshop I attend is to meet one person that I'll keep in touch with later. So hopefully you can meet at least one person that you'll keep in touch with, and we can grow community that way. And as another way to try to grow community, at the end of the workshop at 5:30, if people are interested, we'd be happy to either get some dinner together, walk to somewhere or get dinner, or maybe even order something if we can find a place to sit outside or something like that and just hang out a bit. There is a farm thing at 7:30. So some people are probably going to go to the farm performance at 7:30. So if people want to go to that afterwards, that's fine. Or if people just want to hang out and miniKanren or talk or whatever, I'm sure there'll be some people who want to do that as well.
Okay, and then with that, I will turn it over to Will for your tutorial.
Thank you.
I just turned it off, so make sure to turn it back on.
Oh, okay.
Turn this one off.
So Gabriel, I want to make sure that I'm not turn on some settings on the display.
That they don't what?
You turn off some settings.
Testing, testing, testing.
Oh, sorry.
Hello. Can you hear me? Lambda. Cons. Hello.
It might be closer to your.
Hello. Can you hear me now? No. Is it even on? my voice will carry through the internet.
No, it's not streaming yet.
I think it will be in this. Like,
Okay, it's just people in the back of the room said it wasn't loud enough.
Yeah.
I'll try to get as close. Okay, is that any better? Okay. Okay, we ready? Hi everyone, welcome to a tutorial on miniKanren. I'll go until 10 o'clock, so I've got 47 minutes. I guess the first thing I should say is if you want to learn more about miniKanren, there is a miniKanren.org website, which has this beautiful layout and talks a little bit about miniKanren and has links to, we have to put our workshop up, has links to various workshops and videos and papers and so forth, and dissertations, all that sort of thing. Also has a tutorial, an online tutorial, and a discussion about some of the differences between, say, miniKanren and Prolong. So there are interactive tutorials using live code technology from Nada and Min that you could play around with. So that's a good resource if you would like to learn more. The implementation of miniKanren I'm going to use, so miniKanren is really a family of languages at this point, which can make it a little tricky to know. It's sort of like Lisp. You know, if you want to learn Lisp, the first question is which Lisp do you learn? There are similarities between Lisps, but there are differences. And similarly with miniKanren dialects. So miniKanren tends to be a domain-specific language that has been embedded in a host language. There are standalone implementations, but for the most part, they tend to be embedded in a host language. And because of that, you can pick a host language of your choice, but the implementations of miniKanren differ. The main implementations of miniKanren are in Scheme or Racket, and in OCaml, and in Clojure are the primary implementations. There is I just got louder. There's an implementation of miniKanren called microKanren that Jason Heeman and Dan Friedman came up with. That might be a little too loud. I feel like I'm getting some feedback now. That is about 50 lines of scheme code for the core implementation. And that version doesn't use macros. All you need are either you need like first-class functions or objects in order to embed microKanren into a host language. And because of that, and because it's sort of a standard exercise now when you learn miniKanren to port a microKanren to a host language of your choice, there are now thousands of implementations of microKanren in pretty much any language you can imagine. And at this point, my suspicion, my friend Aziz Ghalom, his claim was that Scheme was the most implemented programming language of all time because anyone who learns Scheme ends up implementing it, usually many times. And for the same reason, I think at this point, miniKanren and microKanren may be the most implemented logic programming languages. Although they're not really logic programming, they're relational programming is the way I view it, which we'll see in a minute. The implementation I am going to use is my sort of go-to implementation. It is called faster-miniKanren. This is an implementation primarily for the improvements by Michael Ballantyne to previous implementations. So that's the implementation I like to use. And I like to use it because it's pretty fast, and also it has a number of constraints that are useful for doing many of the things I like to do, which are things like writing interpreters and type inferencers and that sort of thing, programming language objects. I will point out that at this point there have been many extensions and variants and some tooling around miniKanren. So for example, there's an alpha-Kanren, a nominal logic-based version of miniKanren, which is intended for being able to express things like capture avoiding substitution, which can be a little tricky to implement in logic programming and is extremely tricky to implement in pure logic. In functional programming, it can be tricky, and in pure logic programming, it can be extremely tricky to do things like implement capture avoiding substitution. So that's alpha-Kanren, gives you nominal logic. It's based on work out of Andy Pitts's group at University of Cambridge. There are other implementations. There are higher order unification versions. There's now we have staged miniKanren and a whole bunch of other things like that. And there's been a whole lot of work on the OCaml version out of a group in St. Petersburg, Russia, They've done a whole lot of interesting things with the statically typed Hindley-Milner-based version, but also they have done lots of work in things like proving properties or implementing, semantics and rock and stuff like that. So if you're more into the typed or the sort of formal methods version, maybe look at what's going on in miniKanren. Okay. So let's do just something very simple. I am running faster miniKanren in SHA-Scheme. This implementation also works pretty much identically in Racket. I just happen to be a little more familiar with SHA-Scheme, but I've used both many, many times and pretty much work the same for these sorts of things. So I've started SHA-Scheme, and we have Scheme. So I think people here generally know that in Scheme you can do things like cons up a pair, and you can have a quoted symbol like cat, and you can do things like create a lambda expression, lambda XX, and that evaluates to a procedure, which maybe is represented as a closure or whatever, and then you can apply that procedure you get from the lambda to some value. Now we've done procedure application. So you've got a call by value. Lambda calculus is sort of a standard non-lazy functional language, and it's a Lisp. It's got these S expressions. And one of the nice things here is because we have lists, we can quote lists, so we can say cat, dog, mouse, and we can do things like append or concatenate lists. So this is a standard thing to do. So we can append a list containing the symbols ABC to DE, and we get ABCDE. All right, so we have append. And another thing we have is eval. So eval is an evaluator or an interpreter. Actually, in SHA-Scheme, it can compile. So we can feed in a quoted expression because that expression is being evaluated in Scheme itself at the REPL, read eval print loop. So we want to make sure that we're quoting to a delay evaluation of whatever we want. So I could do something, actually let me just show you a simple example. In Scheme, I can do something like add 3 and 4. Okay, no problem. If I quote the list plus 3, 4, the quotation delays the evaluation or prevents the evaluation. I just get back the data, okay? And for eval, I can go the other way. I can say I want to take the data list plus 3, 4 and treat that as an expression to be evaluated, and we evaluate, okay? And notice it's important I have the quote here, because if I don't have the quote, I'll get the same answer back actually, but for a different reason. Because what's happening is without the quote, what's happening is the Scheme at the level of the read eval print loop is evaluating the plus 3, 4 to get 7. And so this would be exactly the same if I type in eval 7. Okay. So that's just a tiny little bit of Scheme. I'll just show you a couple other things we'll use in a minute. So Scheme has if, and we can ask if a value is the empty list or null. Okay, so I can quote the empty list. If it's null, return 3. Otherwise, return 4. Okay, so we have ifs. We can make choices. Ifs are expressions, not statements. And we also have something called cond. And so for cond, that allows me to make choices. So I can say if empty list is null, return the value of 3 times 4. Else return 3 minus 4. Okay, so that's McCarthy's conditional operator. It allows me to write the equivalent of nested lists in a more convenient form. And then the last thing I'll show you in Scheme is something called let, which you've probably seen the equivalent, even if you don't know Scheme. I'm assuming not everyone here maybe knows Scheme that well. But there's not much to it, so that's the nice thing about Scheme. So I could say something like this. I could say, I want to add x to x in an environment in which x is bound to the result of multiplying 3 by 4. And I get back 24. Okay, so that's pretty much all the scheme we need to deal with. We've seen variables, application, lambda, let expressions, the ability to make conditionals, lists, pairs, and quotation. I will just show, in case you haven't seen this before, because the wording's a little weird. If you haven't seen car and cdr, there's this thing called car, which is like the head of the structure of the list in most functional languages, and cdr, which is like the rest or the tail. Okay, so those are just Lispy names if you haven't seen those before. All right, and then I'll just show you one more thing because this is definitely going to come up. There's another type of quotation called quasi-quote or backtick for almost constant data. Dan Friedman always used the example, Mary had a adjective lamb. All right, and then we can do a let here. So we can say what our adjective is, and I'll say, quote, little. And then I'll put our back-quoted list inside the let expression. So basically this is saying, treat everything within this back-quoted list as if it were quoted, except for anything that has a comma in front of it, which is called unquote. Treat that as if it didn't have a quote in front of it. So the idea is that we'll get back the same list, except for where we put a comma, we'll get whatever the value was, okay? That's something we're going to use a lot. If that throws you for a loop at all, another way to write that is more explicit like this, where you put quotes on things, get rid of that comma. This is equivalent. Okay, so that's all the syntax, all the language you're going to need to know to sort of follow the things I'm doing. I'm going to try to show you, I'm not going to try to teach you every single technique with miniKanren, obviously. I don't have time for that, but I'm going to give you a brief introduction to the language and some of the ideas, and then I'm going to sort of jump to some programming languagey things that we can do with it that I enjoy playing around with, and that sort of get to maybe the promise of what you could do with this sort of technique as we are getting better at doing it. And obviously there are lots of performance issues and things like that, expressiveness issues, but over time we're slowly getting better at these things. Okay, so that's the scheme portion of it. So just remember that miniKanren's in scheme, and so even though I'm going to show you a tiny core part of miniKanren, just be aware that we're inheriting things from scheme. We're inheriting, here's something I haven't shown you, but there's something called define. I could say define x to be the value of plus 3, 4. Okay, now I refer to x is 7. So define is inherited, let is inherited, lambda is inherited. All those things, variables are inherited numbers. All that is inherited. One more thing which will come up, and you're probably familiar with something like this, but there's something called letrec for defining recursive functions. So if I wanted to define append, a 2-argument version of append, which I just showed you, I could do it like this. I could say if L is null, return S, otherwise return cons of the car of L to the append of the cdr of L to S. Okay, so that's my definition. And then in the body of that definition, within the scope of it, I can then call append on my example of ABC appended to DE. And if I did it right, which I seem to have done, I get back the list. All right, so there you go. That's all the scheme you need to know. Actually, with this amount of scheme, you can probably go ahead and implement microKanren as well. You could be able to read that paper and so forth. So that's your starter kit. Those are parts of the language that we inherit when we use miniKanren as our host language. Okay, now I'm going to go ahead. I'll stop scheme because I defined some things. I don't want to have a weird environment. So I'm going to go ahead and load. All right, this is a little weird. MK Vicarious, because there used to be a version of Scheme called Vicari. You've got to load that thing. If you load Racket, you have to do it slightly differently, but there's some instructions on how to do it. So now I have miniKanren loaded. And of course, I still have Scheme around, right? But I have a couple extra things now in core miniKanren. So the first thing I have, well, okay, I didn't show you this thing. We don't really need it, but you should know it exists. In Scheme, there's something called equal question mark, which compares values. So I can ask, is cat equal to cat? Hash T, yes, cat is equal to cat. Is cat equal to dog? Hash F, false. And I can do this with list structures as well. Is the list cat dog equal to cat cat? List cat cat. And that will be false because structurally they're not the same. Okay, so that's the notion of equal. Well, there's something very similar in miniKanren called equal equal. That's why we call it. That's why we pronounce it equal equal. But it looks like this. There are two equal signs, and we can similarly take these sorts of values. So I could do cat and dog. Right? I am asking, is cat the same as dog? Now, if I try running this, I get something weird back. I don't get back true or false or something like that. I get back procedure. And that's because miniKanren is a domain-specific language that Scheme itself doesn't know anything about logic programming, relational programming. There has to be an interface. So the interface between Scheme and miniKanren is something we call run. It's inspired by monads and all that stuff. So we can say run one Q, that's sort of conventional. Q is our query variable. We want one answer if it exists, and we wrap that run expression around the miniKanren code. Okay, so here we're saying, all right, we want to sort of inject back into Scheme land the result of this query, and we get back the empty list. The empty list in this case means there are no answers. We get back lists of answers that really represent, you could think of them as representing multi-sets of answers, probably, the way to think of it. Okay, so we get no answers back. I can make cat and cat equal, and now I get this really funny looking answer, which is _.0. So now my list isn't empty. That means there is an answer. Okay, it means there's one answer, and in fact, I could ask run 2, still get one answer. Run star, which means give me all the answers. We still get the same thing, this _.0 in a list. So it means there's one answer. _.0 means that our query variable Q, which is really what we're asking about, remains unbound. It doesn't have, hasn't been instantiated to anything. So the way you can read that query or think about it is, for which values of the variable Q is it true that cat is equal to cat? And this is saying for all values of Q, that is true. Now, of course, I can change it. I could put a Q in the query. Now I'm asking for which values of Q is it true that Q and cat are equal? Well, in that case, there's one answer. It's like, well, when Q is cat, then they're equal. All right? No problem. And so we can think of it, this first answer, as for which values of Q is it true that cat and dog are equal? Well, there are no values of Q that would make those equal. So that's why we got no answers back. All right. So you've seen half the language already. There's this notion of equality, which is under the hood in this version of miniKanren, implemented as what's called first-order syntactic unification. Unification comes up all over the place, AI, type inference, so forth. It's the same sort of thing. We have what's called the occurs check. So I'll give you an example of that. If we wanted to have the list containing cat unify with cat, that's going to fail. And similarly, if we wanted to have the list Q unify with Q, that will also fail. And the reason is, for Q and the list containing Q to be equal, the Q would have to be an infinite tree or infinite data structure. There are some variants of logic programming that allow this. They allow what are called infinite rational trees, like Prolog 2, for example, allows this. But in miniKanren, we don't. And this is a soundness thing. If you assume your terms are going to be finite, if you don't check for this, then you can produce unsound answers. Prolog, by default, doesn't check for this. So you have to be very careful. So Prolog is really, the defaults are much more about optimization and doing things that are performant. miniKanren is much more about don't do things that are unsound by default, even if it's expensive, because this is an expensive check. So gives a little bit of difference in perspective. Okay, so let me just show you one more example here with equal. So we can have, we can have more than one run variable. So I could say, all right, now I have two variables, x and y, and I have the list x5, and I have the list 6y, and I want to ask, are there any values of x and y for which the list x5 and the list 6y are equal? And the answer is yes. And now because I have two query variables, x and y, you see the answer is wrapped in another list. Okay, so the way to read it is there is one answer, and in that answer, x has the value 6, and y has the value 5. And in that case, the list x5 will have the same value as the list 6y. And I can also change the problem a little bit. And I could say, okay, I could replace the y with x here. What's the answer at this point? Okay, it's going to be empty list. Or I could do something like this. All right, any idea what the answer is going to be here? Okay, can you be more specific when you say anything? Okay, so remember we have x and y as query variables. So x can be anything and y can be anything. All right, so when we get the answer back, notice that we have these underscore dot numbers, but notice the numbers are different. What that's showing is that x and y, they both could be any values, but they're potentially different values. They don't have to be the same value. If I wanted them to be the same, I could add one more constraint. These are constraints. I could say x and y have to be the same, for example. And now you see the numbers are the same. Okay, so x and y can be anything, but they have to be the same thing. So if I unify, y to be, and I can do this in any order, if I unify y to be 7, then they're both going to be 7. An important property of this style of programming is I can reorder my code any way I want, and I get the same semantics. Okay. So that's a very important property, and to me, this is at the heart of the relationality. If you ever break that property, that changing the order of code makes a difference in what it means, then you have left, the sort of the pure fragment of things, unless you have some special semantics where that makes sense. But in all the semantics that we have, that doesn't make sense. Okay, so we've seen equal and run. So the notion of equality is very important. I'll just go ahead and show you the dual to this, a dual to equal. Actually, there's another dual called anti-unification, which I'm not going to show you, but that's super interesting. Another thing we can do is we can do equal/equal, which is a disequality constraint. This is disunification. Okay, so we're saying that in this case that x is not 7. So now the answer is x can be anything like before, but now we have a side condition that follows it saying that x can't be 7. So it can be anything as long as it's not 7. And then y can be anything. All right, and it can be different from x. So that is a disequality constraint. So that is a dual of unification. So we have equality, we also have a type of disequality, which you could think of as a very limited form of negation. That turns out to be useful. We have some other forms of, limited forms of negation. All right, so now let me show you how to make a choice. So before we saw that there was this con thing, McCarthy's con, which is sort of like the ability, to do nested ifs in Scheme. So we have this thing called con-D, which is syntactically inspired by that. So I could say something like, we have a choice where x is 5, and we have another choice, these are different clauses, where x is 6. And if I run these, then I could see I get not one answer, but 2 answers. Okay, so now you can see it's 2 different answers, and the first position are the values of x. Y remains unassociated in both those answers. Of course, I can throw in a value for y if I want. I can say y is equal to x in the first one. And now you can see that we have 2 answers. X and y are both 5 in the first answer, and then the second answer, x is 6, y could be anything. These are independent. Okay, these clauses are independent of each other. Once again, I can reorder these. So I can swap the con-D clauses. That's like a disjunction or an or. And within a con-D, that's like a conjunction or an and. And I can swap those all around, and I get back the same answer. Okay, so that's the important property. Notice the order of the answer changes, but interpret that as like a set or a multi-set, and the order shouldn't matter. Okay. All right, and then the last thing I'll show you is something called fresh. And what fresh does, fresh is sort of a little like a let or something in the syntax. But I could say, fresh xw, and I could say equal y to be the list xw, and then I can say equal x6 and equal w7. All right. Can anyone predict what this will return? How many answers will I get back? 1. Okay. What will the value of x be? Underscore 0. Why? Didn't I just associate it with 6? I shadowed it. Okay, so the fresh allows me to introduce new locally scoped logic variables. So I shadowed the outer x. That's right. So x will remain underscore 0, but y will be associated with the list 6, 7. Right? So this allows me to introduce locally scoped logic variables. All right. And I'll just show you the rest of so you've basically seen all of the core language now. Remember, we inherit define and recursion and variables and numbers and symbols from our host language. I'll just show you 2 more things real quick. So one is we have runtime type constraints like symbolo x and numbero y. So this is basically saying, okay, x can be anything, but it has to be a number if you ever ground it, if you ever instantiate it to a value. Okay, and y can be anything. Y has to be a number, x has to be a symbol. So, for example, if I unify x with cat, that's not a number. Oh no, sorry. If I unify y with cat, that's not a number, so I violated that type constraint. Once again, it doesn't matter how I order these. Okay, I can order the code anyway. The constraints still mean the same thing. So we have some symbolo, numbero, stringo, and then the last constraint which we use, which is a little harder to understand maybe, but I'll go ahead and show it to you. It's a little bit like the disequality. It's called absento. And so absento, we could say something like cat, in X. So what's happening here is that X can be any value, and I'm saying cat doesn't occur inside of it, and cat isn't X. So X could be some complicated tree, and I'm saying that cat doesn't appear anywhere in that. Okay, that turns out to be useful in some cases. We tend to use it as a little bit of a hack, actually. It's probably not that great. It's based on what's called a freshness constraint in nominal logic programming, but without all of the mechanism. Nominal logic programming has a lot of mechanism associated with it. Okay, well that's everything in faster miniKanren. And I will just show you syntactically one more thing, which is a shorthand. You can just use define and lambda, but there's something called defrel. So I will define sort of the canonical append relation in miniKanren using this defrel notation. You could also just say define lambda appendo. It's the same thing. It's just syntactic shorthand. But you'll see like the second edition of Reason Schemer uses defrel, and some papers use it. So I could say conD, remember we had append before, say, well, before we said, well, if L is null, well, here we just do unification, if L is the empty list. Now, the important thing is L coming in could be a fresh logic variable. So this isn't just a check. It's not like null question mark, because if L is uninstantiated, L will become the empty list. Okay, so that's the difference. It could be a check, or it could make L ground. And if that's the case, then we want to return S, but we don't return anymore because we're not thinking about inputs and outputs. We just have arguments. Okay, so LS and L plus S, which is the concatenation, we're not treating L plus S any differently than we would treat L and S. So if we want L plus S to have the value of S, then we have to unify them together. All right, so that's our base case. And then for our recursive case, we're going to have some helpers here, basically. And we're going to say if L happens to be a pair, there's like Lispy, schemely terms, the car and the cooter, or call them A and D. If that's the case, then we are going to say that L plus S is another pair whose head is the same head as the head of L, and whose rest is the result of a recursive call to appendo of D, S, and res. Okay, so that is the definition of appendo. There are lots of tutorials that sort of walk through this in more depth. This is sort of the standard prologue thing. So let me just show you kind of what you get from this. And then we're going to jump from this to something much more sophisticated in programming language-y. Okay, so we're going to do an appendo of, let's do my example, ABC to DE. Oh, yeah, and it has to be Q as my query variable. Okay, so this is what we saw before, right? We append ABC to DE, we get ABC DE, and if that were all the story, this wouldn't be very interesting. But the cool part is I can grab the result, the ABC DE, and I can paste that in to the third position. Okay, so now we get our friend _0 back again saying that succeeds basically for any Q. But the interesting part is that I can now put the query variable Q in a different argument position. So I can say, I want to append ABC to some unknown value Q to get the list ABCDE, and then we can infer that that works for the list DE. And of course, it gets more interesting when I say, hey, I want actually lists X and Y that when I append together give me ABCDE, and here's one empty list to ABCDE. And in fact, I could say, give me all of the lists, okay? And it turns out there's 6 of those lists, and we can we can see what those look like. All right, so this is the sort of thing that you'll find in any Prolog tutorial that's talking about writing programs as relations. And so you could see that one of the nice things is that you get a lot of flexibility. You can also, go further. You can say, I could have X, Y, and Z, or Z, and give me all the values. Now here, if you do a run star, you're going to be in trouble because there are infinitely many. But you can also do partially instantiated values and all sorts of things like that.
Do you mind being interrupted with questions, or do you want to save them?
Sure, go ahead.
So earlier when you had I'll grab the mic. So yeah, earlier when you had the example with absento, and it basically just told us it can be anything so long as cat is absento from it. Is there, so like that's a difference between what, like some of these other examples you showed us where it will like expand out all the different examples of something that satisfies your constraints. Is there any way to get it to like shift between these modes? Like could I get this to show me examples of things from which cat is absento, and like conversely, can I get like the appendo version just to show me a more collapsed like symbolic representation or something?
That's an interesting question. So there is a type of constraint called a finite domain constraint, which we have implemented in miniKanren, for example. It's also implemented in the core.logic closure version. That allows you to kind of do that. The thing about both absento and disequality, if you notice, disequality constraints also kind of the same thing, okay? Those are very weak forms of negation because they remove only a finite amount from an infinite space, okay? The tricky part is you can very quickly get into undecidable type things or programs that diverge. They are expressing sort of negative information. They themselves will not produce answers. What you normally would do is you would combine a program like a relation that's going to generate answers with these negative constraints, and then ideally you would actually prove that no more answers exist, right? Like the best thing you could do is have a run star that has finitely many answers. In practice, unless you're very clever about doing things like adding bounds or you're in a finite space, you're going to have to worry about divergence pretty seriously, and then you may have to think about that hard. But that's an interesting question. I'll think about it more. I'd like to talk to you about it more. But yeah, there are these kind of two modes. There's like the negative information and the positive information.
Yeah, that pattern's familiar to me. So yeah, let's chat more about this after.
Yeah,
Thanks.
finite domain constraints sort of combine both, but the domains have to be finite. Okay, and then the other thing I thought that maybe you were going to mention, which I have to, to be honest, I have to show you the Achilles heel here, okay? Why doesn't everyone write all their programs like this? I'm about to show you. All right, so, and why doesn't everyone, say that this is declarative, okay? Some people do not think that logic programming as done in Prolog or miniKanren is declarative, and here is why. I just swapped the code, right? In fact, I can swap these around. All right, so I swapped my code around, and take your Python program and just start, swapping expressions around, see how well it works. So my claim is I can still go back and do, some of my appendo ones, right? Like I said, there were 6 answers, and well, guess what? There's still 6 answers. But there are only 6 answers. And what do you think is going to happen when I ask for a 7th answer? Infinite loop. And the reason is there are only 6 answers, but by the time I shifted everything around, notice I put this recursive call first in this conjunction. And the extra structure needed to cut off the recursion happens in those unifications afterwards to give it structure. Okay. Now, in theory, it has exactly the same semantics. So we always have to have this caveat. There's like a little asterisk. Reordering the conjuncts and disjuncts preserve the semantics, except operationally, there's this caveat. First of all, the running time could change, or the amount of space taken. But if you reorder the conjuncts, the ands, that you can get difference between an infinite loop versus finite failure, or finite failure versus divergence, failing in a finite amount of time. Okay, that's the problem, and you run into the halting problem all over the place. So if you want to learn recursion, learn scheme. That's my claim. Okay, if you want to learn the halting problem, really learn it. Learn miniKanren, because you're going to run into it like all the time. So that is a serious issue, and so that's a lot of what we deal with is how do we handle this? Are there better ways to do search? Are there ways to prove things? Do we use type systems? Whatever. There are lots of techniques you can use. Oleg Kislyak has really clever ways of using bounds, adding bound constraints, and integrating them in an interesting way. But that's kind of the tricky part. Okay, I've got a few minutes left. I'm going to jump directly to something really cool. So let me load up the and jump into the PL stuff very quickly.
You can take more time if you need it. I shouldn't need my hands.
Okay. Well, all right. I gotta now we're at the fun part. I mean, it was all fun, but this is like, now we're beyond prologue. So let's hold on a second. Oh, yeah. Let's do this. All right. Okay. So if you remember before, I said that we have this eval thing in scheme, right? And so, we can eval things like quote, plus 3, 4, and that will take that list, times 3, 4. It'll take that list times 3, 4 and interpret that as an expression to be evaluated, just as if we had typed it at the REPL, right? Okay, so Dan Friedman's inspiration when doing all the original Kanren work, or the work that led to Kanren and miniKanren, was to be able to implement structural operational semantics, especially for students. He wanted people to be able to play around with the rules that you read in a paper or a textbook or whatever. If you read Types in Programming Languages from Benjamin Pierce, you should be able to take those rules, or you read a paper, you should be able to type in the rules and play with it. So as part of that, when I took Dan's programming languages course, and he showed the scheme interpreter in Scheme, I got very excited because we were also playing around with Oleg Kislyak's type inferencer, that it was a relation, all that. And so I was like, hey, let's figure out how to do eval as a relation. It took a long time, but we finally figured out something decent, help from Eric Holk and a bunch of other people. So we have something called evalo. And evalo is like eval for a subset of scheme, but it's a relation. So we can say something like this. We could say, we are actually, I think for this one I have to say define evalo. This is going to be expr val. And this is going to be all right, now I think we have it. Let's see if I remember right. Okay, so we're going to try to evaluate something. And let's just evaluate something simple like, a call to list, with cat. List with the symbol cat. and that should be Q. All right, hold on a second. I thought it was clever by checking out a new version of the repo to make sure nothing was broken from my experiments, but I forgot that I always put in this code to make this example work. Okay, here we go. It's this expo. All right, now it should work. Yeah. All right, 1 second. Okay. All right, I'll just do it that way. All right, so we have this eval expo. It takes an environment. That's the only difference. That was what I was messing around with. So we have an expression. Here we have, quote, of list of, quote, cat, and we want to evaluate that, and we get back the list cat. Okay, that works fine. But of course, the interesting thing is that because this is a relation, we can say we want to know what the expression is, okay, that produces a certain value. So I could say, I love scheme, right? And so I can generate an expression in our subset of scheme that when evaluated produces scheme. And sure enough, the list quote I love scheme does that. In fact, I can take that answer and run it at the scheme REPL and I get the right answer. It's not that interesting, but I could do like 99 of those. And now I get, some more complicated things. They have various side conditions, but I can kind of ignore those for the most part. And I can just take the expression and I can run it. So now I'm doing program synthesis. And the thing is, I just wrote a scheme interpreter in the same way we wrote append. I had to do it using some of those things like absento and symbolo and numbero to kind of get everything right. But yeah. It's once you have the search and the interleaving and all the other parts that are that you need quite right, and you have the right constraints, then you can write things like the interpreter. Now, the fun example that we always like to do is that what if I wanted to create a program that evaluates to itself, what Douglas Hofstadter calls a quine, right? Is there a way for me to modify this expression to generate a quine, to generate actually, as John McCarthy said, find an expression E whose value is E. Okay, that's John McCarthy's version of the challenge. So how would I change this query to generate such a program? Like that. Okay. All right, let me grab that expression. I'm going to forget the side constraints there, like what are the variable names. And in fact, to make it more readable with these underscores, I mean, this is a very abstract answer in a way. I'll replace the underscore zeros with X. And then when I run it, I get back X. All right. And I can also do similar things. I can generate twines and thrines, and I'll just show you the twines one, or the twines one real quick, because that's fun. Okay, so I'll say I want 2 programs. Larry Moss at IU suggested twines. So I want 2 programs, P and Q and P, that evaluate to each other, okay, and where they're not the same. Because every twine is, these are called twines. Every quine is trivially a twine. I went non-trivial twines. And sure enough, we get this thing. And you can get more interesting structures with this absento, actually. This thing I figured out a while ago. If you do the absentos, you can get structurally more interesting twine. You can see there are all sorts of quotes all over the place. So you can play games like that. All right, so that is one cool thing. So we wrote an interpreter for scheme, and it turns out that, as Stu Holloway pointed out, like, hey, you should be able to generate quines. And then the next thing, which I'll end with, is doing the same sort of thing. I've got another miniKanren interpreter here. I've got one that's a little more sophisticated. Okay, and this should be full interp. Okay, so now we've got an evaluo that's much more sophisticated than the one I just showed you. The one I just showed you just had like had list and quote and application and lambda and variables. It was tiny. So now we're going to have like a much bigger evaluo, the much bigger subset of scheme. And with this evaluo, we have letrec and all that stuff. So what we can do is we could say we want to evaluate the expression where we have append, which is lambda ls, and an if null. So this version of our interpreter has all these things in it. Otherwise, append the coder of L to S, and we will say in the body of the letrec, we'll do our old example, append ABC to DE to give us Q, and we get, what did I do wrong? Oh, I forgot to do the cons. Yeah. Okay. The problem is not miniKanren. The problem is cons of car of L, right? Yeah. All right. The problem is I forgot my intro programming. There we go. All right. So now the cool thing, of course, is this is why you need to know backquote and letrec, okay, to understand this, is that now what I can do is I can take the output, the ABCDE, I can put it in place of the query variable Q. That works. We get the underscore 0 saying it's consistent. But now what I could do is I could start putting things like the query variable inside the call to append. So notice this is append in scheme. I wrote the append in scheme. This is not appendo. This isn't the prologue example. This is just schemes append. But I can do the same sorts of things that I did before. In fact, I can go further because I can ask for a second answer. So sure, the list ABC is an answer, but so is this lambda expression that's variadic, whose body is ABC applied to no arguments. Okay, so you can generate any expression that gives you back ABC. If I want to recapitulate the old version, I just put a quote in front of that expression to say, no, I want actual data there. And then there's a single answer. And I did a run 2, and I got one answer back, so that's a proof. But the cool part is that not only can I play around with this, the ABC part, but I can also start going into the code and say, well, what if I want to replace that coder of L with a query variable? Did I do it right? Let me go back and make sure. Oh, okay, that was a run 2. I'm going to do a run 1. Okay, and then can I do a coder of L? Okay, it's highly sensitive to where I put the variable, but I probably can put it here. It'll come back, but it might take a while. Yeah, so I could put it there. Inside the recursion, it gets more expensive. So that was interesting, and in fact, Michael Ballantyne pointed out, hey, now you can do append, you should be able to synthesize stuff. So then I worked with him and Greg Rosenblatt and a whole bunch of other people to try to make this much more efficient. And so that's the sort of thing we've been working on for a long time. And in fact, there's this Barliman tool. I don't know if I can zoom in on it. So this Barliman tool, which is a front end to what we've been showing in the back end a much more optimized version of what we've been doing, where you can say, hey, I want to synthesize append. I'll just give it a little hint. You don't have to give it these hints. I'll say it's ls. But the interesting part is you have these inputs. So I can say, I want append. I want to have append of empty list to empty list, and that should give me the expected value empty list. And when that runs, it will synthesize a little program. Now that's not the right program. It just came up with a little snippet, so I have to give more examples. But I can say append, say list A to list B, gives me list AB. It'll synthesize. Now it's come up with a null test, so it's like figured out more of the structure, but it still is, hard coding the A and B. So I'll add another example. So I can say C to D, like that. And okay, now it's figured out that it's got to do conses and cars and all that, but it hasn't figured out the recursion yet. So I will add, I'll add one more example, which is EF to GH. There are also ways you can use kind of Skolem variables if you want to make it more abstract and speed things up. So, and there we go. And it was able to synthesize the full recursive definition of append from the examples. The important thing is there's nothing in that interpreter that has anything to do with program synthesis. We just wrote down the relational rules. We basically wrote down operational semantics for scheme, and we get the program synthesis. Now, it's not that we got it fast for free. That part, and to the extent this is fast, that took a lot of work to figure out how to do it. But that's a big part of what we're doing, like with the staged evaluation and other things, to try to figure out how to improve the search. There are lots of things, like the fact that straight miniKanren isn't smart enough to reorder conjuncts when it should in some cases. So playing around with those sorts of things. So that is like a quick overview. We also can do type inferencers and all sorts of other things in a similar way. We have gotten further along, and we are pushing things in terms of constraints. Constraints are a big thing. Also smarter search and machine learning and all these other things, trying to combine those. So I think we have a lot of techniques now, but combining those in an artful way is is challenging. Okay. Thank you.
Do a couple questions if people have them.
Yeah.
What is the largest carbon footprint that any miniKanren program has ever had?
The largest carbon footprint of any miniKanren program.
Yes.
Less than an AI.
Yeah, that's the problem, right? So, I'm talking about any miniKanren, so this is why I'm asking it here, because people here are familiar with many programs.
Yeah.
What is the largest carbon footprint program?
Well, I did do a combinator. I'm sort of obsessed with synthesizing the Y combinator in various ways. And so I did run a program for about an hour that probably had a fairly big carbon footprint. But yeah, I agree. Like in the world of AI, these are pretty small.
How can we have larger carbon footprint?
That's a good question. So I've got a friend of mine who's like, for the animators, for Pixar or whatever, they don't think twice of spinning up 10,000 CPUs for them to render or something, right? So, his idea is that, well, what we need is massively parallel miniKanren running on 1 million cores. And I do have some ideas of how to do that, but it's kind of mega-Kanren, yeah. Carbon Kanren. That's a good question. But that is one thing I've been thinking about is like, well, if you just had huge amounts of compute, someone who has thought about this a lot is Edward Comet. He's got big plans. And he also has a Haskell-y miniKanren-ish language called Guanxi that's designed. I don't think he's working on it right now, but that was part of the idea, is to see if you could scale it up to compete against GPUs. Part of the problem is the way the parallelism works doesn't seem to be fine-grained enough to take advantage of the GPUs in the same way. At least no one that I know of has figured out how to do that. So the parallelism seems less fine-grained. I think there. Okay, so the Chow prologue people. Okay, so the problem is it's like too parallel in a way. Every time you do a Kandi, in some sense, you're splitting the world. But it turns out that if you look at most of the programs, one Kandi clause will be like a base case, which is 2 unifications, and then the other case is like deeply recursive and has 3 recursive calls or something like that, right? And so the tricky part, and the best story I know about, there are 2 really interesting areas if you're interested in this, other than talking to Edward Komet or looking at Guanxi. One is Andorra prologue, and then the other is Chow prologue. Manuel Hermogillo has talked about these things a lot, but Chow prologue has a CIAO, like Italian, Chow. In Chow prologue, you can annotate the big O complexity of each of your prologue predicates in the different modes or whatever. And then the compiler guarantees that the parallel version won't be slower than sequential. It can't guarantee it'll be faster, but given a certain cost model, and a lot of it is this intensity, like, can you guarantee that you aren't going to have these super lopsided, like the problem is you end up with these effectively degenerate trees in the search, right? And so you have to figure out a way to kind of balance those. Michael Ballantyne and Greg Rosenblatt have also thought a lot about this sort of thing. Michael Ballantyne's done a lot of experimentation. So I think there is a way we can do things much better than they have been done, but I don't think people have really cracked the parallelism.
Do something like a long time ago, and I think they more or less abandoned it, so I can't that idea. Haskell Sparks. Where they basically inspect the stack. And so if there's one element on the stack, that indicates that might be too close to trigger parallelism.
Yeah. Yeah, I'm not sure. I think it's worth looking at again. All right, thank you.
Steal these last 15 minutes to give our challenge. Let's see, mic is good. Just realized I might actually have an HDMI cable on my laptop. The general.
Are you streaming at this? Oh, okay.
We streaming? We're good? Okay, cool. So the general, so I guess Will just showed us an alternative to carbon-intensive code generation. For your challenge problem, I'm asking you to explore a little bit of an alternative to, like pre-LLM kind of thoughts about text generation, which I think are still interesting and relevant today as well. In other words, why should LLM people have all the fun? We can also do text generation experiments with symbolic techniques. So if you want to scan this QR code, and I'll put it up again after I overview things, you can take a look at the document on your own time and read it more thoroughly. I just want to try to give you a little bit of an overview before the coffee break. of how I'm thinking about framing this problem, although it's deliberately very open-ended, and you're welcome to kind of reinterpret things as you find them interesting and or amenable to your particular techniques or languages of choice. So this is a relational programming workshop in addition to the miniKanren workshop. I'm kind of the representative of the relational programming at large side. I've recently been working on my own logic programming language called DUSA. So I did a bunch of my testing for this idea in DUSA, but Will tells me this is like also eminently doable in miniKanren, and I look forward to seeing some of how you think about this. So the problem overview is that I want you to think about how to transform some input text to some output text. I don't want to necessarily constrain you to thinking about this as natural language, but I think natural language examples are going to be fun to work with. So the input text might be like several examples. By several, I mean let's say like some small number. You can experiment with big numbers if you want, but I think just experimenting with small to test will be good. So let's say you're just given 2 examples of sentences. The quick brown fox jumped over the lazy dog, and the dog and the cat love to be quick, and they've got some overlap in the words that they use, and you can, and then you want to generate some kind of token sequence as a result, which may or may not make any sense, but that has some resemblance, like uses the same words in perhaps a similar way to the input. The notions of similar here is really broad and again, subject to your interpretation. The simplest one that I like to teach my students as just a very first introduction to what does it even mean to like ingest data and then produce like sentences that are somewhat similar to that data is just Markov models. And the simplest type of Markov model is a bigram Markov model. That just means you're looking at 2 tokens at a time, and you're saying, okay, any token that like if I'm looking at token n, then to generate token n plus 1, I just look at all of the tokens that have followed n before in my training set, and I pick one of those, uniformly at random. That's the uniform part. Now, this will require some approach to like non-determinism or randomness, which you maybe may or may not adopt just from the default search procedures way of giving you solutions. But anyway, so the statistical distribution is not necessarily a thing that you want to focus on, but just doing something where you are looking at previous states and then kind of developing this like state machine transition set between words. And the general theory here is like, if you have more data, you can extend beyond bigrams, and you can look at like the previous k tokens for larger k, and then get slightly more sensible output that may look slightly more like the data. So I have like a sample solution here. I think if you actually want to try to do this yourself, thinking about it for yourself, you shouldn't look at my sample solution. But if you're just kind of curious, like what might be possible, again, this is like a very, very low floor, like very bad solution, and I'm sure you can do better, but I always love to give people bad solutions in order to inspire them to be better. So you can choose to look at that or not. The other idea I want to put towards you is to think about like grammatical categories or parts of speech as you may have learned them, and to consider what it would look like to kind of get an input sentence and then like interpret this as a template. Like if you've ever played the game Mad Libs, where it's like you're given some prompt where you say, okay, give me an adjective, a noun, and an adverb, and it like generates a little sentence for you based on this template. That's what I'm suggesting here. So you just kind of think of this as a sequence of parts of speech, like determiner, adjective, adjective, noun, transitive verb, preposition, determiner, adjective, noun. If you don't know what these things mean, I linked you to a little bit of some background on that. And then generate a sentence with a similar, with the same sequence of parts of speech, which again, this is not like linguistically very sensible, but it is nonetheless something that gives you fun, potentially nonsensical text output that can entertain you. Again, I have a bad solution. And then finally, like the third idea that I concede you with is to try to do both of these in some sense. So like abstract your input tokens, your sequences of input tokens into into their grammatical categories and learn transitions over grammatical categories rather than over specific words, and then generate things that can come out of this like state machine. So here are some example sentences that are valid according to that structure based on the input. Those are my 3 ideas. I'm sure you can come up with better ones. Here's a couple more that I thought of, and if you actually want to think about like natural language, you should look at categorical grammars, and maybe if you want to think about using data, you can look at tree banks, which do some part of speech tagging for you. I also like the tracery tool as a kind of fun inspiration for like making this a kind of ergonomic experience for the user, and just like the way that it interprets this as a context-free grammar and then allows you to generate sentences from it and shows you the parse tree, right? So those are my ideas. Yeah, okay, wow, I went through that pretty fast, so if you want me to explain a little bit more about any of these ideas or the concept or the prompt, I'm happy to take some questions. Or otherwise, I can give you your 5 minutes back and you can maybe start thinking about how you want to work on the problem.
I'll mention that there is an implementation of miniKanren. There are actually 3 versions of it, but the most recent version of probKanren or probabilistic miniKanren that Rob Zinkoff has been working on for a long time. I've worked with him on it on and off for years, and his latest version is based on particle filters. That might actually be a reasonable tool for this, or you can do it in straight miniKanren in various ways. The other thing I'll tell you about sort of the dirty secret of miniKanren, there's an operator called project. If you want to play in the mud and sort of mix the scheme code or host language code with the nice, beautiful, pure code, like if you wanted to do a coin flip or something, you can do things like call project, play in the mud. But it's sort of like using mutation in a beautiful functional program. You have to be careful to avoid destroying all the beauty.
Cool. Okay, good. And you should have access, by the way, to that doc to edit it. So if you want to add some miniKanren resources at the end of it, you should do that. All right, I'll leave the QR code up, but that's it for the Chris and Will show. Thank you. Enjoy your coffee.
Testing, testing. 1, 2, 1,
Hello?
2.
1, 2, 3. Can you hear me?
Yes.
Very good. Let me know when I can
Alrighty.
start, I guess.
Well, welcome back. Welcome to the second session of the miniKanren workshop. Up first, Nikolai Kudasov will be telling us about towards bottom-up enumeration in miniKanren via pruning and memoization. Nikolai, please take it away.
Thank you very much. First of all, let me thank everyone and the organizers for the opportunity to present this online. So I'm going to talk about sort of an experiment, I guess, that that I've been working on, and I'm going to start by talking about why I'm interested in this at all. So we have a programming paradigms course at Innopolis University where I teach, and one of the parts of the course is teaching logic programming with miniKanren. That has sort of displaced Prolog in the past years. And one of the projects that we give to the students is a relational type checker, because that's going to be useful for them in other courses later in the program. And so what we do is relatively standard. We're not the only ones doing this. Is representing a typing judgment as a three-way relation, or at least at the very minimum, a three-way relation with the context, an expression, and the type of that expression in the given context. So one relation, but we have three modes that we run this relation with. There is type checking, which is when all of the context and the expression and the type are known. This is very straightforward to write. And so students usually have no issue writing this. But since this is a relational program, they can also run this in different modes. In particular, the interesting immediate one is the type inference. When the type is unknown, unification does the work, and you get the type inference sort of for free. But there's another interesting mode, which is program synthesis, or type-directed program synthesis, where the expression is not known, but you have the context and you have the desired type of the expression. So here's an example. You can define a context with three variables x, y, and b, x, y of type int, b of type bool, and then you can run run a search for any typed expression in that given context. So with those variables available, and the type of the expression has to be an integer. And of course, it can generate then happily all sorts of expressions within the given grammar that has the same type. However, the problem that you pretty quickly discover as a student, for example, is that some of these expressions are not really making much sense. For example, if b then x else x is the same as x, or x plus y is the same as y plus x. Those are the same programs. And so basically integer type admits all integer expressions. The type does not pin down the program that you actually want. And while the number of distinct expressions, syntactically different expressions, grows exponentially, distinct behaviors of those expressions do grow exponentially, but with a much smaller rate. And miniKanren by default, of course, happily enumerates the same behavior again and again, and we would like to avoid this to actually being able to generate some useful programs. And there are many different approaches to that, including ones that already exist in miniKanren. But if we want to say specifically to give some information about what the programs that we're trying to generate we want to do, we need to give it something. And one example of doing that is giving it the input-output examples, basically sort of unit tests, if you say. So we're going to be working with a simplified example that is worked through in the paper, or at least the draft version that is submitted. So here we have a very simple language with one variable x, two constants 0 and 1, and two binary operations, addition and multiplication. And we're going to be for this example specifically use just the three inputs 2, 3, and 4, and the three outputs based on whatever the program what we want to find. So a naive miniKanren recipe, which is enumerate and then test, is not particularly efficient, but it's very succinct to write. You just generate all of the expressions that you want, and then you select those that you care about with some predicate. Here specifically, the predicate runs a host interpreter on the ground term E, and of course, you might want to also run some relational interpreters or something else. Here today, we're going to be focusing only on pruning and selecting the behaviors based on a host interpreter. Now, if you use this naive implementation and you try to ask for different behaviors and trying to find the corresponding expressions, you can see that, for example, x squared and x to the 6th plus 1 is found in milliseconds, which is fine. But for example, 1 plus x cubed is found in 7 seconds, at least on my machine, and runs through almost 1 million or 500,000 candidates. And if you are asking for 1 plus x to the 4th, which is just one layer of depth lower, it just times out with a limit set to 30 seconds. And the observation, of course, is that for most of the 500,000 candidates for 1 plus x cubed are just rewritings of the same behavior. For example, x squared, x times x, right? Or x times 1 times x, or 1 times x, etc., etc. Which has the same behavior thousands of times when we actually just want any one representative that we find first. And if we look at the space, at the search space of syntactically different terms and different behaviors of those terms, you can see that indeed the number of terms grows very, very fast, and the number of behaviors grows at a much slower rate. So if you are preserving only one, and the ratio, of course, explodes. So non-relational programming by example synthesizers already exploit this gap, and the one of the techniques that that people are using is bottom-up enumeration with observational deduplication. And there are several works where this has been developed, which are referenced here on the slide. So what we do, or what I do in trying to do in my work, is build bring in this functionality on top of an unmodified microKanren core or unmodified miniKanren, sort of. So what I'm trying to bring in is two things. First is a prune combinator that would deduplicate an answer stream by a user-supplied key. And the second one is a sort of version of defrel that would automatically efficiently memorize the relation or table the relation that is compatible with this pruning by user-supplied key. Right. So here's an example. Again, if you look at the body of this, starting from line 3 to the end, that's just standard miniKanren. So basically, compared with the regular definition of a generating relation for expressions, you just replace defrel with defrel/bank. And you add a prune keyword that specifies the pruning key. That is optional. You might not use that, but of course, the idea is that you are going to be pruning by something. So the prune combinator itself is fairly straightforward. You can write it any day, I guess. And it just walks the stream of the given goal with a per call table called scene. The table is just a hash table, right? And the important thing here is that we're doing this per call. That is, if we have, we're going to be talking about nested prunes in a second. A few things to note is a thunk is rewrapped, so we are keeping the thunks, the immature streams. And for whenever we see a state in the stream, we compute its key, and if the key is a sentinel that we call skip prune, that just tells us that we cannot actually compute the key for whatever reason, and we just assume that this we're just gonna treat this state as unique. Otherwise, we just check if the key is already in the scene hash table. If it is, we just drop the state and go forward. Otherwise, we record the key and emit the state. So one state per key value. The whole function is very short to write. I leave out the details here. Now, one thing, there are two things that I guess are worth noting about this. First is the key that we're using. We're using ground key, which applies the host interpreter to a ground term, and whenever the term is not ground, we're just assuming that we cannot compute the key. Now, completeness of the entire sort of relation is up to the key. Every class keeps its first representative. But what I want to mention also is that the fact that I'm using groundness in all of my examples at the moment, this is just a convenience for the demo, not strictly speaking a requirement. And I want to note this because it might be useful to think about keys that are also working on terms with unresolved unification variables. For example, you might be interested in reducing to a normal form modulo logic variables to understand that plus E0 is already equal to E. Whatever E is, we do not need to know the exact value of that. Or, for example, you might be interested in looking for a proof of a certain lemma, and you might not care about the actual proof. You might just care about that the proof or lemma exists or an API exists. And for that, you do not need all of the data preserved, and you might just prune by type, for example. So I have not worked out these examples in details. These are just some ideas that I think are maybe useful. Right, so we keep one deduplication table per call. We would like to also be able to share the deduplication table across nested prunes, which appear naturally in recursive definitions, just like the definition that we have just seen. Sorry, I will just travel back. So here we have a definition of arith bank that defines a unary relation on E, that defines just all of the relations according to the syntax. So it's variable to constants and addition multiplication. And it uses arith bank recursively. So if we define arith bank using prune, the recursive calls are also going to be using prune. So this way we get nested pruning. However, we cannot just share one deduplication table across these recursive calls. And the example is very simple. For example, if the outer prune already sees that we can generate an expression that is a variable, we mark the behavior that corresponds to a variable as seen, and then a recursive subgoal, for example, for the left subterm of plus or times, can no longer emit x by default if we're using just the same table, because we have already seen x, so we should not emit it again. And so in particular, times xx becomes unreachable, and the search hangs because it tries to find terms that we have not seen yet, but it fails. Right. So the important thing here is that whatever we have seen in the outer relation is not the same as what we have seen in the inner relation. So we want the same sort of scene table, but we want to start over it from the beginning whenever we see it again. And so the fix is to prune over sort of canonical variables and then replay that cache whenever we do a call to the same thing again. Right, so, and this is done by def railbank. This is why we need the second combinator, right? So what are the canonical variables? This is something that we just normalize the call of a relation to its most general form when we call it with just n fresh variables, and moreover, to be able to use it effectively, we normalize them to just the variables from 0 to n-1. This is the most general call on the most fresh variables. And so the canonical stream is then the answer stream of that call that we build only once per the external run that is applied to whatever relational program we are running. a canonical cell is one answer in it. And as far as I understand, and I might be not completely correct here, so I would be glad to be corrected. In tabled miniKanren that is described in Williams' thesis, cache entries are what corresponds to canonical cells in what I'm trying to do, except the cache entries can be keyed on different calls, and canonical cells are only cached on the most general calls. And so the differences from classical tabling, as I understand them, is that in classical tabling, equivalence is identity up to renaming, whereas I'm using user supplied key. And the cache indexing is also different. In tabling, it is per call shape. I have one cache for the relation, for the def-rel bank relation, that is replayed later by unification. And what I mean by replayed by unification can be seen on this example where we call arith bank over times AB. So here you can see in the table, in the second column are the canonical cells. So these are the terms that arith bank produces, is x, 0, 1, plus, times, etc. And what we do is each canonical cell is then unified against times AB. And whenever we get a successful unification, that can be used, otherwise not. So we're keeping a single cache for different possible calls to our relation. So then structured arguments sort of come for free by unification. That might have some bearing on the effectiveness, but that's not investigated yet. And fresh variables of the body, of course, have to be shifted into the caller's namespace. So yeah, it's just a technicality. I'm just going to skip over that. So what's important also is that the recursive memoized relations should not hang. And the idea is that it's a standard idea. You first initialize the cache cell and then you evaluate the body. Recursive calls are delayed using the usual what microKanren paper calls inverse eta delay. By the time recursive thunk fires, we already have this cache cell in place, so we do not need to go into infinite recursion. And the recursive call returns the canonical stream itself, so it's the same stream for the general call. So plus two engineering tricks that are described in more detail in the paper. I will not go over them. There's a walk-based replay that sort of sped up the initial implementation by a factor of 2, and a thunk chain collapse. So it's similar to a pull that a client might do to take a value from a stream that may contain consecutive delays. There's also a variant that is described in the paper. I will only briefly mention it, which is the best first variant. It's defrel/bank-w. The W stands for weights. So the attempt here is to fix the bias in the search so that it doesn't go too quickly into deep recursion, which defrel bank has that property. I'm gonna maybe mention it a bit later, but for now, the bank-w is just adding weights to thunks. So we have now weighted immature streams, and we have a best first merge by which never forces the streams. It's just an estimate of what should be the weight of going into this or that stream. So the ceiling is an admissible heuristic. It's just like admissible heuristics in A star, or what also I believe lean-force ASOP uses. Now forcing to pick would re-enter the stream under construction. That slows down things at least considerably, and is not wanted. Just using min heaps does the work, and sort of makes it work. However, there's also a decay factor that you can sort of tune. However, it's not, it doesn't do anything by itself. The exponential decay doesn't really make sense unless you do per production weights, which is when for this is about production rules of the syntax. So, for example, if you prefer plus over times with a higher weight, that would be per production weights. That might make it more practical, and the weights also can be learned from whatever corpus you are trying to use, in the style of Probe, a tool by Barkey, Pelag, and Polikarpova. However, I have not tried that yet, so there's a machinery in place that still has to be investigated more thoroughly. And so there are some preliminary benchmarks that show that the bank method, that's the this column, works sort of well on some, again, toy grammars, but not always. And you can see that, for example, 1 plus x cubed, it runs not faster than, for example, a host implementation of bank, but also just the bounded implementation, relational implementation in miniKanren. So the benchmarks show a mixed picture, and following up on a suggestion by one of the reviewers, I've added to the table the position of the first match in that engine's order. So it's when did we find any representative that matches the behavior? Now, core plus prune is just the first two things without the bank, and it is supposed to be slow. There's it's as slow as no pruning at all because we're just pruning at the end. And initially, I have added this to expect to see the same position numbers as in bank, because other engines fiddle with the order, with the search order. However, as you can see here, that is not really the case. Sometimes we find it earlier than here. Sometimes we find it much later than here. This is still very slow, but again, this is because we're not doing pruning. This is the number in the pruned result. And the numbers are different because even though bank is not intending to change the search order, keeping the same cache and then just replaying the cache actually does affect the order still. So it is faster. It loses on a right biased path, 1 plus x to the power of k. That's one of the sort of biases that bank has. Bank W, the weighted one, actually wins on some string targets, but again, those are preliminary and relatively simple. I have to investigate more. And the host bank implementation, so a sort of a naive implementation in the host that is not relational, also is not always the fastest. It is depth bounded, so you can have some sort of prediction on how bad it can behave. So it doesn't go from 0.1 milliseconds to 2 seconds, for example. There's an upper bound here, but all of the approaches do not compare directly. So what I figured is bounded relational implementation is good when you know the depth and you want predictable sort of search time. Bank, the deferral bank is the default depthless engine, so you do not have to specify the depth that you expect in the beginning. So it may go into the deep end, but for a lot of the tasks, I would expect it to work relatively fast. But again, more thorough investigation of the performance is warranted. Bank W is good for shallow or compact answers. But again, for it to work well, you would need production per production weights. And host bank is if you write it well enough. It's good when you do not need a relational program and you just need to do a bottom-up enumeration. But then again, there are tools for that. So importantly, bounded and bank remain ordinary goals within miniKanren, so you can always use them. The only thing that it do not compose with at the moment is disequality constraints that are also part of microKanren, but that should be relatively easy to fix. Host bank is not a goal at all, so it lives outside the engine. You can hide it behind a member row, for example. So some future work is some more explicit control of the enumeration order, some, for example, depth layered canonical enumeration, iterative deepening, per production weights, as I've mentioned. There's saturation detection. This is something that you can do if you know that the behavior of spaces is finite. And then you can sometimes say that, well, you have already seen every behavior under the sun, so you do not need to enumerate anymore, and you can sometimes terminate early. Constraint stores, like I said, they're not supported at the moment, but it should be relatively straightforward. The key that the user supplies for pruning must just be able to read the store, the constraint store, and the replay must, of course, recheck it. Pruning inside relational interpreted synthesis could be possible, but I have at the moment very little idea of how exactly I would do that. So generally, the general idea is instead of supplying a host language key, you would provide a relational key. But then, yeah, I do not have an idea of how exactly that would behave. And of course, it would be good to test all of this on richer domains and do a proper comparison with current existing bottom-up solvers like EU solver, probe, or bustle. So in conclusion, I've built two small combinators on an unmodified microKanren core to support bottom-up enumeration with observational deduplication and bring this into miniKanren. Prune for just receiving one answer per user supplied key, and deferral bank to get one pruned canonical stream per run for efficient bottom-up enumeration of a miniKanren relation. And so coming back to the to my story where I'm trying to teach miniKanren also to students, for me at least, it would be interesting to see if we can get a more efficient program synthesizer out of the same type checker that students write as in their projects. So this is the experiment that I would like to be able to run in this semester, upcoming semester. We'll see if I get successful. The code is available on GitHub at miniKanren, and the slides are also available online, of course. Thank you very much, and I'm ready to for the discussion or any questions.
Thank you, Nikolai. We're going to take a few minutes, discuss amongst ourselves, and we'll come back to you in, I don't know, 4 or 5 minutes with some collected questions.
I'm currently not hearing anything.
Okay.
I only heard Nikolai.
He can't hear me. Is
I
there
can
a way
hear
where
you.
he can hear me?
I can hear you, yes.
Oh, okay. Then I was
But
just
if someone
speaking too
is
far
talking
away from the
from
mic.
the-
Anyway, we'll be back in about 5 minutes. Do you mind hanging out?
Sorry, I cannot hear anyone now.
Hang on for a second. I'll be right back. 5 minutes. Can you text him? All right.
Seems that there's a very harsh cutoff somewhere, I guess. understanding is that there is a break of some sort right now. Yes.
Cool.
I can
So we've had a couple of time to think up some questions. The first,
Thank you.
Yep.
So I was wondering, first of all, great talk. I was wondering if you have looked into the use of eGraphs for
Off again.
these sort of
Is it-
memoization and kind of equivalence classes. Am I hearable?
it's not just me.
Hello, sorry, the sound cut off and the picture froze from the beginning of the question. Can you
Oh.
repeat that, please?
eGraphs. Have you thought about using
again.
eGraphs for this?
Is that the connectivity issue?
Oh no.
I'm very sorry. If it's on my end, I don't know, but shouldn't be.
Oh, that would work. Yeah.
Yeah, can we type in Discord? The question is, has he considered using equality saturation in eGraphs?
I assume that you are hearing me well, and that is just I cannot hear you well. If that is the case, maybe it would be possible to write down the question and then I can reply. I cannot hear anyone at the moment. I don't know. Let me write down in the chat. Okay. Okay. Okay, I can see questions in the chat. I assume that you can hear me. So, have I considered using equality saturation and e-graphs? Not really. At least not in the first try where I'm working with the ground terms. It seems an overkill there. But yes, for when the key is not necessarily working on ground terms, I think equality saturation and e-graphs might be something useful. Yeah, like for what I named as the example of normal terms modulo unresolved variables. But that would be like way too far in the future at the moment, I think, unless I misunderstood the use case for equality saturation.
No. Somebody press enter soon into the chat.
I did.
Oh, into that chat?
The one he's looking at.
I entered a bunch of stuff.
Okay.
Just try to stop the stream, but I'm still talking.
It's a few seconds delay. It's the
Oh.
question is.
Is that in any way better?
There, it's just delayed?
Okay. Does my notion of tabling include subsumption? What exactly do you mean by that?
What was that movie where
Can you specify?
Yeah.
So subsumption, you mean like when one term is a more explicit version of another term? So when you have, okay. Let me think of that. So what I'm trying to do is I'm trying to get just one representative per key value, right? And it's the key that really determines what we keep in the cache in the table, right? So then whenever we replay that, unification takes care of, I guess, subsumption in particular. I'm not sure that I understood the question correctly, but if my understanding is correct, then the answer is it doesn't have to. That happens on the client side when we replay the thing.
Alrighty. Let's thank the speaker one more time, and we'll take the rest of the questions when we've got internet again.
No, so we table not the most general term, for example, and we do not try to generalize or make a tree of some sort of the cache. We just keep one representative per key value, whatever that user supplied key is. So in that way, no.
Is our next speaker in person?
Yes.
Awesome.
I mean, if you
Let's do a video check. Yes. All right. Shall I begin?
Up next, Andrew Chin's going to be telling us about lightweight runtime security policy verification using an embedded C++ miniKanren. Take it away, Andrew.
Thank you. Yes, that is the title. Before I actually talk about what's in the paper, I'm going to tell the story behind how the paper came to be. So, for context, I'm at a primarily teaching institution. We typically have a 4-4 load, and I've been there for 20 years, roughly. So I've kind of been out of it because I've been so focused on teaching. About a year ago, I was like, oh my goodness, looks like LLMs are actually getting good at making code. Maybe I could actually work on that big project that I would have used graduate students for if I'd had them, because now I can use LLMs. So I just thought about that, and then I was like, yeah, I'll try that. And it had a lot of parts, but one of them was something kind of like Prolog, but breadth-first search. And I was like, okay, is there like a lib Prolog I can just link against that's like a small little library or whatnot? And no, I couldn't find anything like that, and certainly not anything that was breadth-first search. And I was like, okay, well, let's do a little bit more looking. Guile scheme is supposed to be like the thing you link against, and it can't be, and it's not too hard to do like a Prolog in scheme. Maybe somebody's done something where I could do that. And so I'm chatting with the AI about this, and it's like, yeah, people have done things like that, but if you want breadth-first search implemented on top of Guile's scheme, you probably want miniKanren or microKanren. And so that's how I first heard about this, way back at the beginning of this calendar year. And I was like, cool. So tell me a little bit more about this. And the AI's like, it's so small. It's in like 40 or 50 lines of code, this microKanren. And I'm like, well, if it's 40 or 50 lines of scheme, it can't be more than 200 lines of C++. And so I talked to one AI, and I'm like, okay, write a 200 lines of C++ of this. And I talk to another AI, and I'm like, write 200 lines of C++ of this. And then I take their solutions, and I give them to each other, and I say, compare and contrast this other solution with yours. And they tell me about the different features, and I say, I want this feature, not that one. I want this feature, and I keep on doing this until eventually one of them says, the other one is vastly superior, use it. So that was the start of my C++ implementation of miniKanren. And so I'm there with it, and I'm like, yes, I want this to be a small part of my other larger project, but who you want to ask me about during the Q&A, I'd be more than happy to talk about it, but it literally is a completely different paper that's already at a different conference. So yes, I could use it for that, but before that, I should find some case study to just make sure this thing actually works and is robust and mature and stuff like that. So I'm sitting there scratching my head, and even though I'm at a primarily teaching institution, the administration kind of really wants us to chase all the latest fads. And so a few years ago, we did establish a master's in cybersecurity. And so there was this student that was a master's in cybersecurity student who approached me and was like, hey, I hear you're doing some research. Can I do some research too? Because I want to apply for a PhD program, and it'd be really cool if I had a publication in my belt. And I was like, let me think about that. Then I go back and I talk to the AI. I'm like, is there a market for formal verification in the embedded security sector, whatnot? And they're like, yes, absolutely. There's all sorts of stuff. There's some European Cyber Resilience Act and all sorts of things like that. I'm like, I'm not sure I trust you on this, but I trust the grad student to verify what you said. So I run it by the grad student. I'm like, here's what I'm thinking. What do you think? And he's like, yeah, I can run with this. And I'm like, okay, sure. We'll run with this. I don't want to have to think about the security side of things. That's going to be yours. I'll worry about the C++ implementation of miniKanren. And then I go and talk to the AI. I'm like, so how do we divide up this paper so we don't have to step on each other's toes too much? And so he came up with the case studies and the background rationale with regard to the security context. That is not my domain. He did give me a list of anticipated questions and answers. So if you do have security-related questions, I can look at what he prepared. But that's my co-author. So that's the security side. And so that's sort of how this came to be. With that much said, I figured I should so if you're curious, if you want to see the implementation, there's a QR code. You can scan and go there if you want to. The link is also in the paper, which is also off the site as well. So I'll walk through some of the code and what we did and how it worked and timing analysis and the stuff that's in the paper real quickly. So let me go ahead and I will hop on over to, yes. So we have, so when we include the parser, it also includes the core. And so we've got C++ structs to encapsulate the information associated with our security policies. And then we have this policy checker class that will wind up parsing the query, which is the thing that we wind up including, parsing the query, and then we wind up running to see, basically, is it permitted or not? And so that's what we wind up doing. Actually, we don't want security test. We want, oh yeah, we do want security test. And so that's how we wind up doing this. So we do have to convert all those facts over into the miniKanren. And so here we wind up building all the S expressions. And we do that also for the network query. And so here's the main for this test. So we've got the facts in terms of the role facts and the allow facts and the network facts. We have the policy checker, and we wind up running the events by there and sort of seeing, like, how did it go? Was it permitted or a violation? And so we have this for these access control case study, and then we have this for this network policy case study, and then we have this audit query, which is sort of like a join between them, in which we are aiming to find all devices whose role permits read on sensor data, and so we wind up doing all that there. So that's sort of the security side of things. I'm imagining that for many of you, you're perhaps more interested in the underlying C++ implementation rather than the security side per se. Is this a reasonable assumption, or did anybody really want to hear more about the security side of things? It's a reasonable assumption. All right. So in that case, going on in terms of the code. So what actually wound up happening, which I thought was kind of cool, is that what we actually have is a virtual machine, a queue of all the work to be done. And so we have, here, let's make this bigger. We'll make that even bigger. And so we have a queue of all the work to be done. And a lot of the decisions that I made in terms of how things could be was I really cared about performance and I really cared about memory features. It's really quite nifty. We can do everything with bump allocate, bump deallocate, and compacting tree-like structures. And that's it. Like there's nothing else to be done in terms of memory stuff. Everything's trivially destructible. And whatnot, which I found to be really cool. And it's almost entirely iterative because we're working off of a queue that's managed in an arena. The only recursive parts are the tree compaction, and there's one other place here that's recursive. Otherwise, it's almost all iterative, which my hope is that we'll all fit. The instructions will all fit in the level 1 instruction cache. That's my goal because I really care about performance on this. But let's head on to the showing how. Here we go. So for example, for the disjunction, we wind up pushing it onto the queue, and then, and for the conjunction, we wind up pushing one onto the queue with a continuation because they have to share the environment. And so, I think it's actually kind of nifty how this wound up working in terms of that. So that's a little bit of the core. I won't spend too much time digging through all the implementation here. There was one other part here in the slide. We do the here actually for context. What I should probably do is here in the core. This is a number of lines of code. And so you can see it's not that many lines of code. It's not that many lines of C++ code because most C++ projects wind up being way more lines of code than this. And so I'm actually quite pleased that we managed to make it as relatively small as it was. I'll spend just a little bit of time looking at the parser. It's relatively simple because it is S expressions, and so we do have standard S expression stuff. We have symbols; they get interned in an arena, so there's a separate arena for the symbols to be interned in. And otherwise, it's sort of standard things you'd need for S expressions. This does use C++20, so if you're used to C++, you're probably not used to things like this. This is fancy lambdas in C++20, context capturing lambdas. It's kind of amazing what they've done if you've not coded since C++11 or earlier. But yeah, so there is that stuff. But otherwise, it's relatively straightforward implementation in terms of various things. So that's the core. That's the S expression. Other things. Let's see. I suppose I should actually go ahead and run that security test. So let's go ahead and do that. If you want me to, I can recompile it. But it runs really fast. And as you can see here, we have microsecond counts in terms of these tests, with various ones being permitted or violation or whatnot. So yeah. So my goal with this is keeping it small, keeping it high performance, and hopefully making it so that way we can embed it in lots of things. The security was just the case study that came my way, but I'm hoping we can do this in lots of other places as well. I do indeed have that other project I was envisioning that is certainly the one I want this to be part of, which, like I said, is part of a completely different paper, but you're welcome to ask me during the Q&A. And so with that much said,
Can I ask an implementation?
absolutely.
If you rotate it, turn it red to green.
Yes, you can certainly ask me questions now. In fact, I
Okay.
was just about to get to that.
Thank you. So, well, it's not even exactly an implementation.
Sure.
It's sort of a design question.
Yes.
So you chose to implement rational trees and unification over rational terms, which is has been done before for miniKanren, but it's a little unusual. And I was curious if you could talk a little bit about that and how that interacts with soundness and correctness proofs, and whether or not you have any issues related to correctness or soundness, given the fact that you have these infinite trees and there's no assumptions in your system that the trees are finite. You don't have to do the occurs check or anything like that. Is that correct?
That is a great question. And because so much of my design process was a back and forth between me and AI, there are certain design decisions for which it gave me options, and I said, I don't really know what would be most efficient, and went with it. I chose C++ as the language of implementation because I was confident I could debug it because I had years of experience with that. But in terms of implementing unification of anything, I'd never done that before, to be honest.
Okay. Certainly, if you can avoid the occurs check, that can be very efficient. It has all sorts of implications about correctness and soundness that ripple throughout the system when you do that. So,
yes.
Yeah, I'd be curious more about that story and how it affects everything.
Right. I mean, I suppose in context, maybe I should show a different case study that's sort of more involved.
Okay.
So yes, so I will go ahead and do that. All right. So this is the idea is that we're playing a game of memory, also known as concentration, where you've got certain cards face down, and and you get a choice of which two to flip up, and then if they're right, then they're matched and they get removed, and if they're not right, you put them down, and then you can try another two. Have we all played memory of some sort before? Yeah. So this is a simulation of that, and so we capture things like given a board in a position, what is the value here? I should note that we don't have we don't have condi or condu. We only have conjunction and disjunction and fresh in this implementation. So here we have a value at, and then here we have trying to match. Are these not equal? And then here we have a list of all the positions. Then here we have one to find all the pairs, and so then we need a helper. So we then do an accumulation style thing and whatnot. And then in this sense, this probably starts to look oddly like, well, how would you have done this if you'd written it in Scheme? And so in some respects, this winds up looking perhaps like a more convoluted version of how you would write it in Scheme, except this isn't Scheme. And then here we have one that, given a board, a fixed position, and a list of later candidate positions, finds every later position that matches the fixed one, if it was there. And then here we have a helper that has a sort of similar structure. the point that was made earlier about how order matters, like order really does matter. Earlier versions of this had all manner of issues where, you know, the recurrence was being done before the quality check, things like that. And so we wind up having this sort of programming discipline that had to come about where your typical relation winds up getting defined with a disjunction, and then within there are conjunctions, and then within the conjunctions, the very first things that you want to have are the things for which all the terms are already bound and they're going to fail, so they can fail quickly so that you're not going to explore that branch more often. And so then here we have the top level one that gets all the position and goes to find all the pairs. And so this is sort of some of how this has come to be, and the types of things that have come to place. So, you know, it is entirely possible, it is actually quite likely that the ways in which I'm envisioning search space are ones that don't hit upon nuances of unification types. Does that answer your question?
Should we let a brief response? About the yeah, I'm not sure if it answers my question. I guess I have to look at the paper in more detail. I know that there are rock proofs of correctness of the algorithms. What I don't understand is, are these just correctness of unification as opposed to properties of the overall system? Because,
right,
you know, your unification, I mean, it is fine to have unification over rational terms. That's a fine thing. What I'd be curious about is the properties for the overall system, if that's affected. And also for efficiency, there are things like, well, I saw that you did have an implementation of Robinson unification with triangular substitutions. I guess you're not using triangular substitutions for the rational unification algorithm. I wasn't able to pick.
I believe that's the case, yes.
Okay. So I was also curious if there's things like environment trimming or, you know, sort of garbage collection over substitutions, if you're really worried about the efficiency, if you had considered things like that. But I guess that's my main question that I'm not sure I understand. I'll look at the paper more, but you know, you can have a bunch of correct you know, algorithms, but the overall system properties you get may not be what you think unless you also are proving properties at that level. So that was the part.
Fine follow-up discussion.
Yep.
Yes.
Okay. Thank you.
Do we have any more questions? And we can line up.
Just a really quick one is you stated, I think, your goals for doing this implementation were, and using C++, were to make it both compact and therefore embeddable and also fast. And I'm curious if you have any sort of, or if I missed them, I'm sorry, if you have any performance benchmarks or anything that sort of stack this up against, you know, people have written schemes to be fast before, but maybe not specifically with solving in mind. So that you really might have the edge, but I'm curious if you've got any numbers or anything.
Yeah, that is a great question, and I probably should do that. I think one of the things is that, like, and this is part of my question to you all as the miniKanren community, can we have a standardized, like, benchmark test suite that I can just, like, run for these purposes so that I could actually know what would be a good way to measure? Because that was actually one of the things that sort of crossed my mind, is like, I'm sure I could come up with something for which this would be better, but it's also entirely possible I could come up with something for which something else would be better. So if we could have, like, the miniKanren equivalent of SpecInt 2000 or whatever, you know, I would be delighted.
Great answer, yeah. Yeah, so my understanding of your application is right now you have a database of all the policies in your IoT system, right? And you use the miniKanren to do a reasoning to see, okay, this is a policy, is the acceptable word. So have you think about to detect the confliction in the policies?
Oh.
So for example, the ACL will say, okay, some nodes will allow to access the HTTPS in one rules, and then in this junction, the other rule says, okay, you cannot access it. So basically here is some conflictions.
Right. Yes. So yes, currently this is just about policy enforcement, but sort of policy consistency checking, internal consistency within the policy set. That is definitely anticipated future work that I'm hoping we can do not just for this, but also for other sorts of environments like configuration management and other sorts of things like that, where we do have these sorts of rules of like, if you choose this option, it means this doesn't apply, but if you choose this option, it means this doesn't apply, sort of thing. Yeah, so that's anticipated future work.
Yeah, because on the paper I saw you mentioned about answer step programming. So basically in this case, you should choose the whole policy as the whole database. And in answer step programming, you'll be unsatisfiable if you have contradiction rules. Yeah.
Right. Yeah. Understood.
Can you help me understand what you said about allocation, memory management? You said something about how all you need is bump allocation. I thought I knew what that was until you said bump deallocation. I have no idea what that is. And
Right.
and then there's something about tree compaction. But is that, yeah, like, can I get some understanding as to
Yes.
why that's all you need?
Okay. So yes. So all the memory, anything that's allocated is allocated in these particular arenas. And so here we have the arena management stuff. And so everything's allocated with this alloc. And so most of the time, if we're doing anything, we are either allocating or resetting. And that's sort of it. And so in this context, here in this core, the only bump deallocating would be the resetting. So the arena, so the pointer that is at the end that we would be bumping to allocate space, the reset is we just bring that back down to 0, back to the beginning.
How, but when do you reset?
When do we reset? At the end of a query and before the next query. Yeah.
So you just sort of keep allocating, and it will, like if there's a lot of solutions, you'll just keep generating them, and at the end of the query, you're like, okay, exit the process, kind of like I'm done.
Sure.
Okay.
So we do that.
Yes, that's how to answer my question, isn't it?
Yeah.
So there's no call to resetting what you should.
Right. There is no call to reset here in the core. If we look in some of the test things, it would be so that the core is there just to implement a query, and so the other things that use this would be the ones that would call the reset. Yeah. So there's the bump allocate. So there's the reset, and then the tree compaction winds up being in these deep copy. And so we've got deep copy term, deep copy goal, and in certain circumstances, those will be mutually recursive with each other. And so that's the only sort of tree compaction, tree copy part.
Yes, so one more question about the relational programming parts, because you mentioned about you want to use the relational programming things. But on your paper, I saw you only one direction. Like right now, you have the device, you have the policy, you generate a result is permitted or violated. So are you able to, for example, I give you a new IoT device. I want to say I want to access the HTTPS. I want it to be permitted. Like which region should I put in? Are you able to generate it right now?
That is theoretically possible. We do not have code implemented to make that happen on the C++ side of things because of how we encode things. But in theory, that shouldn't be too difficult. You know, because you know literally all our security code is here in this.
Yeah, I think right now if you implemented miniKanren correctly in your C++ engine, it should be built-in. Like right now, if I want to run the query to say, here's the device, here's the result I want, which region
Right.
should I put into?
Yeah, yeah. So that should be a query that we could build, and so here's a call to reset for you know, but that is a thing we should be able to build and run, you know, as a query there. Yes.
All right, let's thank our speaker.
talking to this one? Will this work? Okay. All right, so we're going to get the afternoon session started with Dmitry Volkov, and he's going to talk about all for one and none for all. He's got all the syllables in there, and the word array was floated, so I'm excited.
Sounds good. All right, thank you for coming. This is all for one and none for all, compiling polymorphic relations without monomorphization. Let me sit down to get in the camera. So yeah, I've worked on this with Yafei and Professor Shan over there. Let's get going. So for the overall structure, we'll introduce the miniKanren language, which we're working with here, and then how to make it polymorphic. All right, so as a brief overview, miniKanren versus miniKanren, where miniKanren evaluates very roughly over searching over a stream of values usually. miniKanren instead evaluates via multidimensional array operations and combining them. miniKanren is usually dynamically typed, sort of built up on an S expression structure, where miniKanren is statically typed with finite algebraic data types. In miniKanren, relations are usually unweighted, and there are some exceptions, some experiments, but miniKanren relations are usually weighted, so different branches of a program can have more weight in the output. All right. So polymorphism, as you might know, is when we can use the same code to operate on multiple different types. In particular here, we use type variables to represent what the different types can be. But as mentioned, miniKanren represents relations as finite multidimensional arrays. So what polymorphic relations need to do is represent arbitrary many specifically typed relation arrays. So how can we use a single array? How can we use an array representation to represent this potentially arbitrarily many specifically typed relations? All right, so we come to the slogan. We have a method to represent all of these specifically typed instances of a polymorphic relation using only one single instance of the polymorphic relation. And we use this as a compilation pass to get rid of type variables, getting rid of the for alls. All right, so going more into detail about the miniKanren language itself. So say we have this graph we want to represent, 0 is connected to 1, and so on. We can either represent that as an adjacency matrix, which is pretty common for representation. So here we have our from dimension and our to dimension, and we have a 0 where there's no edge and a 1 where there is an edge. So we have a connection from 0 to 1, and we have from 0 to 1, we have a 1 in that position representing that edge. Alternatively, we can represent this graph as a relation in miniKanren. So here our domains are the from node and the to node. They each have type here num4, which is a number 0, 2, 3, because we have 4 nodes, 0, 1, 2, 3. And then either we have the from node is 0 and the to node is 1, so the same edge as before, and so on for the rest of the edges. So what miniKanren does is it computes this kind of array representation, or this kind of matrix representation for arbitrary relations. So just pointing out here, so from is num4, to is num4. They're both number types of size 4. And here, both dimensions of the array are also correspond to number types of size 4. So they're each dimension has size 4. All right, so miniKanren programs are built up of primitive relations and combinators. So here our primitive relations are equality and disequality. Equality puts a success value where the two values are the same. So when x is 0 and y is 0, we succeed. And when x is 0 and y is 1, we fail, as you'd expect. Disequality is really easy to implement when we're working with finite sizes. We just put a 0 where the values are the same and succeed in the other positions. Disjunction is semi-ring addition. So here, either x is 0. That's everything along this dimension is where x is 0. Here, y is 0. Then we disjunct them. We add them together. And we get this array where there's a non-zero value in any position where either x is 0 or y is 0, and a failure everywhere else. Here we do have a 2 in the position where both x and y is 0. This is what I meant by relations being weighted. It could be thought of sort of where, I guess, traditional miniKanren could be thought of as a set semantics. This could be thought of as a bag semantics or something. But I guess the convention is for 0 values to be treated as failure and non-zero values to be treated as success. All right, conjunction is multiplication, same sort of thing. X is 0, y is 0. Multiply these two arrays element-wise together, and we get a success where both x is 0 and y is 0, and failure everywhere else. Fresh is interesting. Fresh is handled by summation. So for an example, we have our graph from before, and let's say we want to calculate the incoming edges of the vertices that have an incoming edge of this graph. So that would be 1, 0, and 3. And 1 has 2 incoming edges. So here we have our graph from x to y. We sum over the x-axis, which is the vertical axis of this relation. We squash it down. And we see we have 1 incoming edge for 0, which we do. Is that one there? 2 incoming edges for 1. Those 2 right there. And 0 for 2, and 1 for 3. So fresh is handled by summation. One way I like to think about fresh is as a disjunction over all the values the variable can take. All right, so going back to the graph example from before, how do we actually compute this? We start at the bottom, compute those arrays, and combine them using conjunction and disjunction as I've described. So here we have 0 is our from, 2 is our 1. We multiply those together, and we get a 1 in that position, which is our 0 to 1 connection in the adjacency matrix representation. So on for 1 to 0, and so on for 2 to 1, and so on for 2 to 3. All right, so those are the matrices we've calculated for each step. We now have a disjunction, so we add these matrices together, and we get our adjacency matrix representing the graph as expected. All right, so briefly talking about the type system, miniKanren values inhabit algebraic data types. In particular here, we'll focus on sum types. So a sum type takes 2 subtypes, and it's either one type or the other as the sort of nested type. So we use left and right to represent those 2 cases. So here, left 0 and left 1 take up the 0 and first positions within the left part of the type, and 0, 1, and 2, corresponding to the num3 type, take up the 0 first and second positions in the right type. What's nice about some types is that they actually take, with the left and right naming, is that they actually take up the left and right part of the vector. So it's pretty easy to just look at the representation and see what's going on. miniKanren also supports unit and product types, and the num type that we're using here is shorthand for a sum of unit types. All right, so that's the basics of miniKanren. I'll talk about how to make it polymorphic. So as a motivating example, we'll consider this sum swap relation. And what it does is it takes 2 variables it takes 2 arguments, and they're related if the inner part of the arguments have the same value, but the outer sum type is swapped with a left for a right. So here, x is left of 0, and y is right of 0. And so they're both 0 on the inside and left and right on the outside. We have a 1 there denoting success. Similar thing down here. X is right 2, y is left 0, 1, 2. We get a success there. The inner parts are the same, and the outer part is swapped. And just sort of zooming out, we can sort of see the structure of this built into the matrix. So this part is where x is left, y is right, and the inner a's are unified. So x is left, y is right, and then the inner parts are unified. We get that identity matrix structure. And then, same thing in the bottom left corner. X is right, y is left, and then we get that identity matrix structure. All right, so what if we consider the slightly larger example? That was sum swap where the sum type is over two num3 types, but we could also consider sum swap where one of them's a num4 type, so it's a slightly larger version. We get the same behavior as before. The inner value stays the same, the outer value is swapped, so x is left, y is right, inner value is the same. Same thing down here, but we have a larger size, so right 3 and left 3. 3 is the largest value of num4, so we couldn't get that before. But overall, the behavior is the same. So, and yeah, the only difference in this piece of code is that some 3s from before are now 4s. So it'd be nice to abstract over this to be able to represent this in a more general way, not needing to specifically define it for every type. So here's where we get polymorphic sum swap. And the only difference here is that instead of specifying these concrete num types, we're using type variables to represent the types we want to swap. But that, of course, leads to the question, what does the array representation of this polymorphic sum swap look like? So going back to the slogan, we represent all concrete instances of a polymorphic relation using only one single instance of a polymorphic relation. And we use this to compile away type variables. And so how do we actually go about doing this? miniKanren computes a small array. This is our all for one, this is our one array. And then it expands it when we have a relation call to the needed size of the new types. So each expanded array entry takes the weight from one entry in the smaller array, where both entries have the same equality patterns of the values at that entry. Excuse me. So miniKanren uses this technique to compile away type variables. Sorry, let me get some water. All right. So how do we actually go about expanding sum swap here? So just first to observe some sort of general structure that's shared across these two matrices. We get failure in any position where x is left and y is left. That holds for both of these matrices. And we also get failure for anywhere where x is right and y is right. This holds across the two matrices. We don't have the swap in either of these cases. We get a success when x is left 0 and y is right 0. So x is left, y is right, and then the inner parts are the same. So here, 0 correspond to the sort of alpha-typed part in our polymorphic sum swap. And the alpha-typed parts of these two values are equivalent in both of these cases. And that holds for anything along the sort of upper diagonal. X is left, y is right, and the alpha-typed part of the value is equal to each other. So here, it's 0 for x and y. Here it's 2 for x and y, same on both sides. On the other hand, we get failure when x is left, y is right, and the alpha-typed parts are disequal. So here, the x is left 0 and y is right 2. 2 is different from 0. And same thing in the top right. And that holds for any of these places in the upper block where the alpha-typed parts are disequal from each other. We get the same sort of pattern in the bottom right, where x is right, y is left, and the beta-typed parts are equal. That holds even in this case, where I guess beta is I guess the value is 3 for both of the things. So even though we don't have a case where the value is 3 here, it maxes out at 2, it's the same value held within the x and y. So here it maxes out right 2 and left 2. Here it maxes out at right 3, left 3. But the point is that they're equal in both cases. And we get failure anywhere the beta-typed parts are disequal from each other here. So same sort of thing. All right, so looking at this at a more higher level, we get the same success and failure results in both the smaller and larger matrix when the non-variable typed parts of the value are the same, and when the variable typed parts have the same disequalities across both matrices. I guess equalities or disequalities across both matrices. All right, so that brings us to the idea of equality patterns. So when do things have the same structure that I've been talking about? How do we break it down? So as mentioned, so I guess here x is right 2, y is left 2. Here x is right 3, y is left 3. The values are different, but both of the values in these positions have the same equality pattern. So x is right, y is left. So the non-variable typed parts of the values are the same for both of these matrices. And the beta typed parts here are equal at both of those positions. So both of these, I guess, positions have the same equality pattern. We'll look at this position now. Again, the values are different, but the equality patterns are the same. X is right, y is left, so the non-variable type parts are the same. And here, 2 is disequal from 1, 3 is disequal from 2, so the beta-typed parts are disequal from each other in either case. So they have the same equality pattern, because in both cases, they're disequal. All right, so here x is right 2, y is right 0. Here x is right 3, y is right 0. Again, the particular values are different, but we still have the same equality pattern. X is right in both cases. Y is also right in both cases. So here we have different types on the inside. We have x is of type beta on the inside, and y is of type alpha on the inside. So we can't actually compare these. It would be a sort of polymorphic comparison, which is outlawed by the type system. So we don't need to compare the inner part here. There's nothing to compare. What matters here is that the outer types are the same across both matrices at those positions. All right, so we have shown before how we compute non-polymorphic relations bottom up. And we've shown how we can compactly represent a polymorphic relation using this sort of smaller structure and then expanding it. So are we done? What are we missing? So as the leading question might make you guess, expansion does not always work. There are edge cases. So consider this relation has this equality where we take a value of some variable type, we create another value of that type, and we check if they are disequal from each other. So in the case where alpha is num1, a thing of only a type that only has one value, we get failure because there's only one value the x can take, and it won't ever be, I guess both x and y have to be the same value because there's only one value. So the disequality thing here fails. On the other side, if alpha is num2, there are two values that x can take and y can take. So the disequality always exceeds because for any value of y, x can adopt the other value to get the equality to success, the disequality to succeed, sorry. So here we have a matrix that fails in any position, and here we have a matrix that succeeds in any position. So expansion does not work here. When we're looking up entries in the same equality pattern, we can't look up a success from a matrix that only has failure in it. So what this means is that we do need to handle small type sizes separately from this expansion process. So it's not actually all for one. That said, it is almost all for one, in that once you get past a certain large enough threshold, you can represent absolutely anything past that threshold with the single relation. But for the small matrices, we do need to handle those separately. So it is a little bit of a lie, but almost not a lie. All right, so what does the compilation process look like here? So we've talked about how to replace polymorphic calls with concrete monomorphic relation calls. So calls that are at large enough type sizes, they all use this. They all call the existing small instance of the relation that represents all the structure we need. And then small calls use the correctly sized smaller version of the relation when doing a call. But before we do that, we need to calculate the sizes for which this all works out. There's more details about how to do this in the paper, but it basically means accounting for making sure that we have enough room to do the disequalities as needed. And then once we have the calls, we use the expansion process to turn monomorphic relation calls at the, we turn the large enough calls at the smaller size. We use the expansion process to expand it back to the correct type sizes. All of this is done by generating vanilla miniKanren code that I've showed in the beginning, so we don't need any new special constructs for the language. It's done as a compilation pass. And more details about this in the paper, including a sketch of a proof of the correctness. And then there's a separate paper with a full proof. All right, so what would this look like? So say we have this not very useful relation called equal, and all it does is check that its arguments are equal. Obviously, we would just use the built-in equal in practice, but for demonstrating compilation, it's a useful small example. Then checking equal 3434 would become something like the following. So we'd generate fresh variables for the larger type, which here are x1 and y1, and then generate fresh variables for the smaller type, which here are x2 and y2. We'd make sure we'd set our arguments appropriately, so x1 is 3, 4, and y1 is 3, 4. We'd call equal at the, we'd call equal specified to the num2. This is sort of the small version of the relation that we're calling. And we'd call that with the x2 and y2, which are the smaller sized type variables. Then here we enforce the equality pattern between the small sizes and the large sizes. So if x2 and y2 are equal, then we want x1 and y1 to be equal. So they have these are the variable typed parts, they're alpha, and if they're equal in the smaller matrix, we want them to be equal in the larger matrix. Same here, if x2 and y2 are disequal in the smaller matrix, we want them to be disequal in the larger matrix. So this is how we enforce this equality pattern structure. All right, so that's roughly the whole thing. That's how the process works. More details on the paper, of course. So in conclusion, we can represent the equality and disequality structure of relations compactly and then expand this to larger sizes as needed. Part of the reason this works is that equality and disequality are the only primitive relations. So does this approach generalize as we move into the discussion? Some things to think about. Does this generalize? So in this presentation, I've only showed relations with at most 2 arguments or dimensions to the array. Does this generalize beyond that? As a hint, yes, it does. As another thing, how would this work with recursive relations, in particular open polymorphic recursion, where a relation may call itself at a different type than it itself was called? And this is monomorphization cannot handle open polymorphic recursion, because then it would need to generate potentially infinite relations. But does this work with that? As a hint, it does, but fun to think about how. Does it generalize to more than equality and disequality? What about to recursive data types and to non-relational languages? I don't have answers for those yet, so would appreciate to hear any thoughts. There's the GitHub link. I think that's about it. Yeah, thank you very much. Wait, I think we're doing the discussion first. Is that how we're doing it? Table discussions? And I can walk around. No. Yeah. Yeah, and I can feel them.
All right.
Okay, so after a brief delay, we've got Eridon Domoratsky, who's going to show us some cool stuff for unification in miniKanren.
Hello, can I start?
Yes.
Thank you. Hello, my name is Eridon, and I'm going to present you our work about rational unification support for miniKanren. So I would start with some small motivation example about encoding finite automaton in miniKanren. So what if we need to write a relational verifier for some regular language with finite automaton? It would look like something that. So we have a relation which consumes our state and list of symbols. And if the list is empty, we need to check that the state is a terminal. And otherwise, we need to look up for transition and go next. So how to represent the automaton itself? The simplest solution is to use some named representation where the automaton would look like list associative list where every state had its name and some flag of terminal and list of associative list of transitions. But this representation not so cool because we need to pass the automaton, the full automaton in each call, and we need to consume more time to look up for each state. And moreover, when we want to run our verifier backward, we will face problems with names, which adds unnecessary structure. So what if we represent automaton as pure graph structure is in memory directly without names? It could see like that, but there is problem with cyclic data structure in memory. And currently, miniKanren is not allowed to deal with cyclic terms which need to encode such a structure. But it is more direct to use such structures in problems like that. Okay, so what is rational term especially? First of all, we have a well-known notion of terms, finite expressions of variables and function applications like that. But we may also consider possibly infinite terms of same structure, and especially we may consider special case of infinite terms where the term is required to consist of only finite number of subterms. In this example, there are only one subterm, while every subterm is equal to the whole term. Infinite terms generally are relevant for computational logic like miniKanren or Prolog because we are not possible to deal with infinite terms directly, but a rational term is a great corner case which is helpful for us here. Okay, yeah, so why we need rational terms? Except for considered example above, we have type inference where recursive types are directly representable with rational terms. I'm sorry. And for example, we may generate programs with some kinds of fixed points like imperative ops or recursive functions. For example, Y Combinator is representable by rational term directly too. So since all of this may be represented using additional names like before, the rational representation more direct and not add unnecessary structure. Some notation which I use in the presentation that set the set of variables, the set of functional symbols or constructors, the set of terms, and triangular, especially substitutions. These all notated as on slide. So if we look inside fast and miniKanren, we may note walk primitive like on the slide, which is just check the term for its shape, and if it's a variable, it's try to resolve it using the substitution, and if the variable is unbound in the substitution, it just returns the variable, but if it is bound, it continue walking inside the term. The next is just extension primitive. It's trivial but notable since it performs an occurs check. And finally, the unification algorithm itself, it is just rewritten from the source code of faster miniKanren, but the key point is that we first do walk on input terms and next pattern matching on the results of walk. So to achieve rational unification, we first need to remove occurs check. But if we just remove the occurs check, we face infinite looping because when the substitution I'm sorry, when we face purely recursive term or rational term in the substitution, we just go inside it infinitely. this is because of these calls for walk, not only from them but from them too, because these walks prevent us from checking for the source terms before walking. So let us consider also implementation of unification in miniKanren. It is different in one place, which is the signature of the walk primitive. It consumes not term but a variable, and we first trying to resolve it, and next we deal with resolved term. So how this changing the algorithm itself? We don't do walk at the first step. Instead, we first pattern match of on the terms, and after that we use walk on variables. This is just a micro optimization, but it's useful to take into account which we may distinguish between source term shapes before walking. And there are two different approaches to achieve rational unification. The first approach is to remember equivalences between non-variable terms. Essentially, this means that we will remember how two instances of term in memory, which are some objects in memory, we will remember how they are related between. And to do this, for example, in sweprolog, each term instance have memory cell where another term instance may be linked. And before recursion, before recursion, the sweprolog interpreter just dereferencing this cell to ensure that the terms are not linked before. And I call this approach is Hewitt's approach, which is used in most implementations of rational unification. But there is another approach is to remember only equivalences between variables, which is more like more like what we do when we deal with finite terms. And since the last case, which relates to non-variable terms between staying the same, other two cases become much more complex, but we we are going to look inside them. So first of all, we need to slightly improve our walk from previous variant to return also a variable which was the last variable in the dereferencing or invoking chain. So this variable will help us to distinguish between different equivalence classes inside our equation system. And this is similar to the find operation of the union find data structure. The next, we need to define union. Union is similar to union from the union find data structure, and it just unioning or something two equivalence classes between two equivalence classes by variables, just like in the union find. But there is one difference that each equivalence class may be may have right-hand side non-variable term, and when two equivalence classes have right-hand side, it is clash because we unable to save them both, and we need to return them to the core. Okay. Next, we need the common part primitive, which just takes the common part of two terms, and it's essentially it means that we looking on top of two terms and checking them are similar with respect to variables. No, I'm sorry, modular variables. Okay, and returning their common part, which ends with variables. So finally, the algorithm itself is using union in the two variables case. And when we have a clash of right-hand sides, we just resolving it using a recursive call. There is also a helper function for variable with term case, which do something more complex. It first checking for the variable, is it bound or not in our equation system. If it isn't bound, we may just add binding. But if it is bound already with some other term t first here, we need to take the common part of the existing right-hand side and of input term. We need to do this to simplify and first to simplify the right-hand side of the equivalence class, but more important that this is required to split complex cycles in terms on parts along the variables. So okay, I hope it is clear. If not, I'm open to questions at the end. Okay, how we have evaluated it? First, we have test cases which are bunch of unification traces, where every unification trace is a list of equations between terms. We have two automatically collected test sets from existing OCaml-based solvers, which are Java generic solver and Llama type checker, where Java generic solver uses only non-rational unification, but Llama type checker in some cases requires rational unification too. And we had synthesized um, some test cases for interesting corner cases. For example, full binary trees unification, which is consumes exponential time on the convention on the I'm sorry, on the conventional unification algorithm, and left is tree vs right is tree, and unification of many loops like x equals to f of x. And we have compared between three algorithms: the conventional unification, Hewitt-like unification, and our described above unification. The main result is that if we compare between rational unification algorithms, if we compare them with the baseline and between them, we may see that in ephemeral implementation and in persistent implementation, in buff implementations, our algorithm is positioned nearly to the main diagonal, which is I'm sorry, which show us that this algorithm is as fast as the conventional in much cases, but the Hewitt's algorithm faster in implementation, in ephemeral implementation, but slightly slower in persistent implementation. These plots uses logarithmic scale, so this ratio of Hewitt's algorithm is non-constant. It is logarithmic too. Okay. What about rational tests? We have not so much because we have no so many real world solvers which need rational unification. But on these cases, we have a similar situation where in ephemeral implementation Hewitt's algorithm better, but in persistent our algorithm is better. And at the end, on synthetic tests, for example, the tests where we trying to unify leftist and rightist tree between, we may see that Hewitt's algorithm much slower than our, which is because we are unable to use numbering on term instances like we may use it on variables in variable age heuristic. Okay. At the end, we have presented rational unification algorithm and show that it is appropriate for using in miniKanren. We show that algorithm performs as fast as the conventional in non-rational unification problems. Also, we have shown that the UX approach is inappropriate for miniKanren since it works at bad in persistent settings. And moreover, even in ephemeral settings, it not so not so great in some sophisticated synthetic tests. We have open implementation which shows not only the evaluation results from the slides and from the paper, but also different different approaches for implementation. Our algorithm too, simple implementation and optimized implementation, which was used in tests. And also we have full certified implementation in ROC, which is mirrored from the practical implementation to be sure that the proofs are relevant for the practical implementation. Thank you very much. I am ready to ask some questions. Hello?
Yeah, so we're
I
going to
don't
do
hear.
like a discussion here and then ask questions after that. So there'll be what, like a few minutes discussion, and then we'll come with our questions on the mic once we're done with the discussion. So if you can sit tight and we'll get back to you. Yeah, do we have any questions? Questions? Yeah, yeah. Well, I'm asking the room if there's any questions.
I have one very simple one.
You should do it. Yeah, so we've got some questions we're gonna run by you now.
Are rational terms the same thing as cyclic terms in Prolog, or is there some subtle distinction between the two?
Which terms in Provoke? May you repeat, please?
Cyclic terms.
I'm not sure, since in Provoke, especially in sweep Provoke, every term is rational. Is rational until you do unification with occurs check on them, because rational unification works faster. But I'm I'm sorry. I just
Yeah, it sounds like the same then. Yeah. Okay. Thank you.
So I may add that the implementation, practical implementation of Hewitt's algorithm was studied from the actual source code of SweepRovog, since it is not easy to read PhD in French, and first I've studied it from source code in C.
Thank you for your talk. My question, this is Will Bird. My question, which I asked everyone, but I'll ask you, I think it's more appropriate this time, is it's fine to have an algorithm that is sound and proved correct and all that, but when you're using that algorithm in a bigger logic system, you have to worry about soundness of the entire system. And if you're not using the occurs check, there are certain things that you might run into. For example, if you implement a type inferencer for simply like typed lambda calculus without the occurs check, you'll have things like self-application will type check. So my question is, I guess, two parts. What are the applications that you hope to use in the future beyond, finite automata? Do you have bigger plans? And secondly, is there a way or rules that are in place to use rational unification in a way that doesn't result in soundness problems?
Okay, thank you for question. I think we may use rational unification as a main algorithm for unification in miniKanren, with exceptions. And in my plans is to build some miniKanren system which will be based on rational unification, to be to not be slow due to occurs check when it is not necessary, but when we need to restrict some term to be finite, as you talking about self-application or something, we may use some other extensions, and first of these extensions is just using different I'm sorry, binders, different binders, not fresh, but some other kind of fresh which will mark variable this that it must not be recursive, but it is not convenient in practice, I think. And there is another option is to extend the miniKanren itself um, with inductive and co-inductive goals. So co-inductive goals need to use more effective, more efficient, more effective. I don't know, to use rational terms in practice. You may you may hear about it or read about it in core LP paper, but also in similar way we may define inductive relations which are required to not be to not be depend on its more general variant when we call it. So when we use so inductive relations, we may guarantee that we will not recurse infinitely inside it, but also for the topic we may use inductive relations to restrict finiteness of terms, like define inductive predicate list, which will check that the list is finite and not infinite. And I think it is the next step to extend miniKanren with rational unification to add no, such extensions to more effective working with it. But it is all in plans.
All right, thank you.
Thank you for question.
Okay, and I think that's about all of our time. So thanks very much.
Thank you. I can disconnect, yeah?
Welcome to the miniKanren Workshop 2026 keynote, presented by my academic brother, who graduated from Indiana University under Dan Friedman, as I did, my co-author of The Reason Schemer, second edition, and the co-creator of miniKanren, which is probably the most implemented logic programming language in history. Jason will be telling us about a lean, mean miniKanren machine. I have no idea what that is, but it sounds cool. Jason Heeman is currently an assistant professor at Seton Hall University in New Jersey, where I got to visit and see all the interesting things going on. And Jason is one of the motive force personalities behind miniKanren. So we're very happy to have him here. Thank you very much, and I wanted to learn what a lean, mean miniKanren machine might possibly be. Thank you.
All righty. Thank you, Will. Yes, so I'm doing this with no notes. We'll see how that goes. Also, I should caveat this. This is work in progress. Nothing to do with the lean theorem prover, but I do have a student who's implementing some of this in Rock right now, so who knows, maybe the title's enough inspiration to get him to switch. So I should say this is joint work with Bryson Fingston. He's an undergraduate senior right now, and he's presented some of this stuff last year at the miniKanren workshop and then more recently at FLOPS in Japan. And we've extended it a little bit further since then. So just quick little bit of a get it going quiz. Little query. Everybody should be able to read and understand. My question to you is, what's the list of answers that you get out? The world's foremost experts in miniKanren in this room right here and online should, of course, be able to tell us the answer. No, not you. Skip it. No. Okay. So there's something kind of tricky going on. For a surprisingly small implementation, these languages have some very complicated semantics. And we wanted to be able to illustrate how it is that the Kanren-style search works and how it is that you can get programs that are this short and this sophisticated. Let me ask, if this was depth-first search, do you think you'd be able to tell me the order? So there's some additional complexity here that I think is worth looking at. So let me pull up part of our answer to how to understand this. And it's a GUI tool where you can start stepping through the execution of a search tree of binary conjunctions and disjunctions. And you can watch the delays propagate upward. And if we keep going, we'll eventually find that the first answer we get out is that fish answer, and they'll keep going from there. So the rest of this is that in more detail. If you've got somewhere to be in for the next 35 minutes, you've seen the essential part. So furthermore, I should say, the answer is fish, turtle, dog, cat, at least if you're using the implementation that Dan and I published last time at 2023, but we know that when you place delays in different places, when you change how you associate conjunctions and disjunctions, all of a sudden you get very different behavior. So yes, I was cheating and throwing you all a trick question, and I don't apologize for it. Beyond just that, why should you care about understanding miniKanren's answer order? If we want to reason about productivity, starvation, fairness, if we want to do some miniKanren compilation and we want to have some notion of what it is that we're preserving, if we want to be able to have tests that we can reasonably test, is my program still giving me the same answer, then whatever sensible notion you have that doesn't allow absolute starvation, like the set semantics does, has to be some weakened version of representing answer order. So that's a good place to start. Yes, you guys have seen our little demo. Another part of the story, when, as I understand it, when Will was first learning miniKanren, what he wanted to do was to implement all of essentials in miniKanren. And by the way, everybody, Dan says hi. My version of that was I wanted to do the PLT Redex book for miniKanren. What does it look like to treat a miniKanren language like you would treat defining a calculus and a directed reduction relation and then machines for miniKanren, the same way you would have for the lambda calculus? The recipe from the PLT Redex folks is basically this. Define the expression language, choose some subset of those expressions, call them the values. Define some primitive notions of reduction, close them to obtain a calculus, and then eval is some subset of the cross product of the expressions and the values. And we know what this looks like for the lambda calculus. We've seen this and studied. This isn't a perfectly reasonable picture for how it is you might build a semantics for a language, specifically this kind of reduction semantics out of a calculus. And so then, what does that look like for miniKanren? What's the example? Carry out the SAT analogy. A first blush, you might think, for our previous example, something like fish or turtle or dog or cat. Maybe these are the values. But we said that the values have to be subsets of the expressions, that there's some miniKanren program that this evaluates to. I can't think of a miniKanren program that resembles something like fish itself. That's not quite the answer, and neither is substitution. I want some notion where we can step redex by redex and produce what we call a value. And we were thinking about this, and right, there's a relation environment, but ignore that for the time being. And miniKanren's an expression-oriented language, so we should be able to take an arbitrarily complex expression and redex by redex produce some unsteppable thing that's a value. And at the very least, we have, once you take off the surface syntax, I know of one thing that's certainly going to be an expression in the language, and that's the query. And our answer was that if you step redex at a time, what you end up with, starting with this ugly search tree query thing, is a normalized tree, a list of answers. And so that's the first thing that I think of. As you're describing this as a reduction semantics, you should imagine the query and such things like it as members of the class of expressions, and your reduction is making it look more and more like a list of answers. The things that we wanted to preserve, to be able to think about, were the emitted answers and their order. We also wanted to represent the unfinished search. We wanted to mark where variables were freshened, which ones were freshened where, and we also wanted to mark where delays had been executed. And we also wanted this to be the case that you should be able to, for this expression, separate it into a context and a redex, take a step, go around again. I may have said compilation or removing the surface syntax, but that's not, we know, not quite as trivial as I made it sound, dispensing with in one line. There's a whole lot of research that we've done and gone into figuring out where should you put these delays or how should you associate these operations. There's a whole lot of these choices that you can make, but I want you to think about that as like compiler flags for options that you make, and the real program that your runtime executing is what you get when your cond macro and your defrel macro have finished expanding. So think of that as the actual query that you're executing. And so now I'm going to talk just about what those search trees look like in a little bit more detail. Here's, for example, the model the goal syntax might look like for equations, introducing fresh variables, binary conjunction, disjunction, delay, and a succeed and fail goal, so that you know that's basically what I've got. There's nothing up my sleeve. When you have a disjunction goal and a state, that should produce, when you small step somehow, whatever it should do. It should end up with G1 with that state and G2 with that state. And now I want to talk about the little yellow box. So see that as a constructor work for our little model. I want something with a tag on it, and I want some little box where I can hook some information. It's a nice, pretty picture. There's a constructor associated with it. Likewise, conjunction should be able to split into two pieces. We have G1 with the state and then G2 waiting. I'm drawing it like this to kind of highlight the asymmetry of conjunction. Fresh variable introduction. This is a little bit different. Marking the nodes where we introduce the logic variables, marking the logic variables there. I'm not putting any of that information in the state itself like we might have normally done or done in other representations. Here we're keeping an ordered list of the variables that we're introducing. Call it the own provenance record if you want to be real fancy about it. And you can't see it here, but that's sitting inside of my work constructor. So right now we've got this language of goals, and the one search tree node that we have is work with a goal and a state inside of it. Now we have a second one. The goal succeed immediately steps to some other kind of a search tree node. Here this one's green because it's good because it worked. Returned, and the fail goal steps to a state dead. This is what I just said, but in a form that's executable in PLT Redux. So we're keeping a lists of binders. I made it one fresh variable at a time here, but we actually have it so you can do multiple of them. So writing a program doesn't require freshening this many and being off the screen in the GUI. That's our language of these work contexts that we've got so far. Work grammar nodes that we've got so far, and these three are atomic. The part that I didn't show you before is what happens when you step this disjunction node. You keep the provenance record here on the disjunction, and the two goals start with an empty work provenance records. Again, that's what that says here. If work with some own provenance record and a disjunction goal in this state steps to a left-pointing disjunction with that same own provenance record, and we'll have sub work trees, G1 and G2 in that state. Conjunction does what you'd expect it to do if you've seen conjunction before. So I wanted to talk about why we've got this somewhat more complicated infrastructure of goals and search trees and things, and it's because you need to be able to separate three different regions that you're discussing. So these goals that are pieces of the program that your user gave you, you can't reorder or rearrange that. Above that are pieces of the search tree that perhaps you do need to reorder and schedule, change according to some scheduling policy. And that's what we're talking about here. And then above that is the portion of the settled answers where you can't rearrange anymore because all the computation's been done and you have them in that order. So search tree, conjunction, disjunction nodes, the conjunction and disjunction of goals, and then some way of illustrating that we've got this answer and then this one and then a search tree with more work to do. The way execution works is we rewrite step in that search tree, bit at a time, producing more answers until we end up with nothing left to do, and we have, if we're lucky, a last answer. Or we might have, if we tried, and the very last thing we tried, maybe we freshened a bunch of variables, we had to step a couple of thunks, but ultimately failure. Maybe it ends up with this done node. The ownership stack moves to last, and this answer node just begins with an empty list. So finding the redex is then walking down the spine, and then walking down the work path until we get to the redex. We should be able to make a quick switcheroo, and then go back again. So we're looking at the composition of two contexts down the spine, basically walk right down the spine. Then for this one, walk left down the work path for any disjuncts until you come to the next thing that you can do, and then take a step there. When you get an answer, finally somehow bubbled up to the top, by the top I mean this more constructor is marking where, okay, that's the end of the completed answers, here's the spot where there's more work to do, here's where the search tree stuff, the actual things we can flip or delay are. When you have a disjunct node with a returned answer as its left child, then that moves to an omitted answer with a search tree of more work to do with the remaining disjunct. So it's taking a search tree disjunction and moving it up into an answer list disjunction. And if you prefer the executable rules, there it is. So the stuff that I haven't shown you, pending delays, forced, and the emit syntax, if you want to see what it looks like in the redex model. But it was my contention that people would like to see the trees better, so if you appreciated seeing the trees move around better, then you've made my case for me. So, delay. When we execute a delay node, it marks as pending with still a goal in that state waiting to execute. And yeah, I mean, work turns into a pending delay. And at a delay, this is where the scheduler choice matters. Most of those things that I talked about where you place the delays, associativity of conjunction and disjunction, these are compiler flags. How you schedule the search, that's really choices of runtime behavior. So for a depth-first search, we will, in this model, turn that into a pending delay with the more work to be done underneath it. Just in case you've missed it, what I'm telling you is that, so interleaving depth-first search flips and moves the delay up. So what I wanted to point out here, in case you missed it, is that we can model both depth-first search and this interleaving depth-first search using the same grammar, the same semantics, the same model, because the way that we're representing depth-first search is when you come to a delay, go to the top and depth first search means come back down and invoke that delay. It's the same delay, execute, it's just doing it in the same depth first search manner. And when you finally have that pending delay cross, then the forced it here marker also crosses onto that spine. So along our spine, we're recording variables that are shared amongst an answer and then the rest. Each of those gets marked on the node where they were introduced. The places where we executed a thunk to continue the computation get marked, and we're tracking all of those on the tree itself. We haven't talked about relations or relation calls, and I think it's kind of neat that you can model all of the behavior that's really interesting about miniKanren search without having to represent the relation calls themselves. Once you, with a couple reasonable restrictions on you choosing where you're going to place those delays, as long as once you model delays themselves in the system, then you can just add the relations as a separate environment, and like you would look up an environment in any other kind of a language behavior. So this is saying adding to the list of goals. We also have a relation call calling some named relation and a list of arguments. I've now defined a program to be, instead of just an expression, some expression together with an environment of named relations, but there's nothing interesting that has to go on in the semantics of looking up relations. All of that's already captured in the semantics of executing miniKanren goals. This should be bog standard. Second little extension that we added, it was somewhat annoying for users looking at and trying to follow these trees executing, to have for the interleaving depth first search the trees when you execute flip-flop, 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 flip-flop all the way back up. That just got kind of tough to look at, and Michael Ballantyne suggested this approach where rather than flip-flopping the children on the way back up, why don't you add a second kind of disjunct node so you can keep the trees the same and use these kind of he knows more about trains than I do, and for some reason these reminded him of something on a railroad switch, where which way you're going to go down the tracks. And this was a small extension to the language, and if you add that extension, then you can implement this railroading style as a third behavior. This is the GUI that does this, that Bryson and I talked about, or that Bryson's presented, and we've worked on since. It's got a couple of neat features that I wanted to highlight. One of them is bidirectional source mapping. So you, yes, ma'am?
Sorry, did you already talk about
unification, equality? No, I totally skipped it. Okay. That's completely fair. Great question, by the way. Anybody else, keep them coming. So I'm treating unification atomically. It's a bit higher than like the Warn abstract machine would be for that. So unification is single step. If the two terms unify in that state, then it steps to what was it? Starts with an R, answer. I just said it. Well, whatever. It's dead if it fails, and it's a returned answer if it works. Sorry, good question. So bidirectional source mapping, you can click on the tree and it'll take you to the part of the program that you wrote, or you can click on a goal, and if that goal is once, twice, or multiple times in your tree, then all those instances will be shown so that you can look at what part of the original program I wrote has led to this, this syntax tree here. We're noting when you've succeeded. You can hover over, and there's a tooltip describing the reified representation of what it looks like at that state so far. And you can also look in and see what logic variables correspond to it pieces. The model of that program is that there really is a PLT readx model in the back end. The front end's JavaScript, and that interacts with the Racket API. And so when you're watching this GUI step, this isn't just a visualization, it's actually a visual representation of an executable semantics. That little cache in the middle isn't doing much that's very sophisticated, but if you've played with readx models, you might have encountered that it's annoying to have to step back and then step forward, and so we keep the previous states. It's nothing more than if you step backwards, look back in the list, and if you step forward again, we don't have to recompute the forward state. Alrighty, so this is a lot for a GUI, and what all does this now let you see? What can you look at and understand that maybe you couldn't before? I think that the right way to understand a lot of things is this notion of a controlled comparison. Take two related presentations of a thing, or closely related things, align the parts that play the same role, hold the common parts common, and then what remains unmatched, go focus in and study that. So if you wanted to see how interleaving depth-first search scheduling compares to depth-first search, it's nice that you have a common language and a common grammar for search trees in which either of these two scheduling policies work. If you wanted to convince yourself that the interleaving depth-first search behavior and the railroad model give you the same search semantics, you can put those side by side and see it. Something that's new that we didn't have before is that we've coded this in readx also as a modular search semantics. So there's a small core of conjunction, fresh variable introduction, and your atomic goals. And then, there's, I think, 13 total steps that you need to understand. 13 total reduction steps: how you allocate fresh, how you expand a conjunction, how you handle returning an answer, how you handle failure. For local execution, succeed, fail, and the unify goals. And we also had disequality, and what do you do when you get the final answer. That's everything you need to understand the core language. Those are all the steps. Delay and disjunction can each be represented as deltas, as add-ons on top of that core language. And we can represent that in readx doing the same thing. So we can make executable the relationship, how you think of these different features. That's actually executable in the semantics. The scheduler fibers put on top of that. This search join, this is a pure additive join. There's nothing interesting that happens here besides just the combination of what happens when I add this delay feature, what happens when I add this disjunction feature. Pick a scheduler, and the relation environment and relation calls are a little bit on top of, once you've got delays, it makes sense to add those. For 21 total rules, and if you wanted to watch how a miniKanren programs small steps, if you can understand 21 rules and you can follow those trees, then you can watch it step by step execute. As I said, it's kind of neat to have how do you add a feature. The suspend goal how you add a pending delay to the work, and places where we forced. We had 3 different pieces to the tree that you needed to look at. Adding delay has asked us to add a new goal, something new to the search tree work, and then something new to the place where we forced. This is just to prove, nothing up my sleeve. We are taking that core language and lifting our the reductions from core up to that extended delay language, and then we're unioning that new reduction, that lifted reduction relation, with the new rules that we've added. Yeah, so to add a feature, we have to add its tree forms, the reduction rules, and also update any checks and tree walks. This is not just for the semantics, but also if you're checking well-formedness, whatever observations you're doing. And we should be able to add delay and then add disjunction and then add delay, and that should work either way. Cool. I've shown doing logic variables in a way that if you've ever looked at the microKanren stuff is a little bit different. Normally we store a counter in the state. This model gives you both more precision in places on exactly recording where variables were freshened, but that's important if I've got a conjunction and I record this is failed. When I pass up, I need to, when I reduce this conjunction and I'm tracking the variables that were used there or the variables that were in scope, I'd want to annotate that this conjunction, because this first conjunct is dead, this whole conjunction is dead, and I want to store that these were the variables that had been introduced during that time period. Until we eliminate it, we're going to still execute the entire list of variables that had been introduced during that failed process. That was something that didn't do originally, didn't think about, and it was only when we did some of the later work executing different models or trying to compare different ways of accounting for logic variables that we realized, oh, actually, you need to fix this and do this rule differently. In our model, we've implemented this with 3 different kinds of carriers for logic variables. One of them where we represent on those search tree nodes the owner provenance records, every one exactly where those variables were freshened, and this gives you a kind of structural information for where the logic variables came from. But this should be, in some way, a more detailed representation than if I had just kept in the state itself a record of all the variables that we've introduced. We have the variables that we introduced at every place in the state, but at that point we no longer have recorded where it is that those variables, where this one was introduced, where this one was introduced, where this one was introduced. We just know the order. And having that ordered support is more detailed than just keeping track of a counter. If you wanted to reason about fresh variable introduction, then maybe the microKanren isn't the right model to work from. Maybe it's this earlier model where you're tracking exactly where those variables were introduced. Have an explicit accounting for where the delays were forced. And it might be that you'd do your proofs about that model, and then I'd want to show that the executable model that I'm using is some forgetful representation of that thing that we know has the right proofs for it. So as I said, we've implemented our production semantics parametric in these 3 carriers. just another neat point that I think is worth underscoring in this model is we've represented non-determinism as data. We've taken a non-deterministic search behavior, and by fixing a scheduler, we have now represented the state of that search as data where the execution of that scheduler on that search tree is deterministic. Once we pick the scheduler, the whole tree tells us what happens next precisely. There's exactly one regex. All right, so what happened to that PLT regex book? So there's this nice paper from Donvey 2008 where he says we've got, describes a beautiful pipeline starting with the reduction semantics. This is the same kind of pipeline that the PLT regex books walks through. If you have a reduction semantics, then you can do refocusing and transition compression to get a small step abstract machine. And if you do fixed point fusion, you end up at a big step abstract machine. 4 deterministic languages. Until now, maybe you all knew this, I had no idea why can't I make this same kind of regex pipeline work for me. And it's because I didn't know how to treat miniKanren as a deterministic reduction semantics. This lets me do it, and parametric in the scheduler. And while you're at it, heck, why not parameterize the representation of free variables? We are some part of the way through doing this, and so I'm going to tell you some, but not all, part of the way through doing this, rather than having to, as we said, decompose, contract, plug, decompose, go to the top, decompose again. We should be able to, by refocusing, have your contractum and regex pair, step 2, next contractum and regex pair, step 2, next contractum and regex pair. This is a beautiful theoretical way to describe it, not the nicest execution. So we should be able to, turn the crank on now that we have this model and get us to a nice, pretty big step evaluator. And it would be cool if that big step evaluator happened to in some way correlate to the interpreters, the natural semantic style thing, that we would, in the C311 style, know how to CPS defunctionalize, registerize, and turn into an abstract machine. If they don't coincide, then there's something interesting there too. What related reduction semantics does it end up at? Or is there some other way that we could be thinking about presenting miniKanren semantics as an interpreter that gets us this nice picture? We can represent our miniKanren behavior as streams, but we should also be able to think about it as as success, fail, delay continuations. Do those two models line up? Which of those two do we end up, or do they end up at the same thing? And these are questions you can ask once you have multiple representations. Forgive me if this is overly grandiose, but it was the example that came to mind. I think it's cool to have multiple different presentations like this so that you can compare them, put them side by side, and see what's missing. What do you benefit from understanding, from taking type theory and looking at it through the lens of logic? Maybe there's something the logicians knew about that we didn't have on the type theory side, or vice versa. Maybe we can, by having other ways to produce these kind of artifacts, see where they line up or see where they don't. For any of those, for like the core language or just the delta of adding delay part, or just the adding disjunction part, we should be able to take those same steps of reduction semantics, decomposition, and all the way down to our big step machine. We should also be able to forget information about how we're representing our logic variables, and any place along this axis there should be a correspondence. We should be able to look and see, is it actually the case that I can transform I can transform just my core language, transform the delay delta part and then combine them together, and that should work the same way as if I had added delay onto my core and then done my machine transformation. If we're doing it right, then those things should commute in the obvious way. The box diagram should let you get to the right place from both directions. There should be, if we're not keeping track, I said structural here, but secretly I've been calling it sprinkled, the version where the variables are sprinkled all about. We should be able to get rid of those records and really just keep the little counter that I was calling as the lean version. And if you'll allow me for mean to be base or simple, then there should be both a lean, mean, miniKanren machine waiting here at the end. The story is, I think we've been able to expose the different choices that you can make in your search as structure. We should be able to, now that we have this deterministic semantics, derive machines. And we should be able to compare all the different positions on that three-dimensional grid thing, three-dimensional-ish grid thing, and make sure they all commute in the appropriate way. So if you want to try the stepper, it's there. If you want to play with the code, it's there. Thank you all very much.
Do we want to do discussion style Q&A this time too, or?
You know, Jason, what it's like? Which one would you prefer?
Oh, I don't care. I would love it if we all talked and asked questions as much as possible. I would love it if you all got in a circle and told me what I was doing wrong and what was a bad idea and how to make it better. Was any of that the options that you had in mind?
I guess the question is, do you want us to discuss first, or would you
Oh yeah. Anybody got a good question now? Okay, well, I tell you what, why don't we give it a few minutes and then we'll come back together and people can line up and do it like that. What do you say? Yeah, cool, and will the session chair let us know when it's time to gather all back together?
Am I the session chair? Who's the session chair? I can set a timer.
Okay.
What are you going to do?
I'll do 5 minutes? Sure. Okay. All right.
the thing to work through, and there's seems like a trade-off there. So at least for the core language and then the addition of the delta disjunction, delta delays, that part works, but it's not a very nicely fused together machine. And I think I know how to do the machine, but then I don't have. Do you want a pretty machine or do you want pretty proofs? Yeah.
Jason, can you unmute yourself?
Are you pointing to me? Yeah. Okay, cool. Hi, this was very, very cool. I am also very highly motivated by, like, we need some operational semantics for our logic programming languages, and have done a kind of similar exercise with my logic programming language that I'd love to tell you about later. But my question is kind of going back to this question of how you represent the unification, and it makes sense to think of this as atomic if you're doing things as matching. So I think of these kinds of things from the perspective, sometimes from the perspective of if we're doing well-moded logic programming. So like our inputs are always sort of known when we're sending them into relations, and then we get outputs out, and then we can use those as ground inputs for the next thing. Then things are like very nice, but like in miniKanren, you're not always in this situation, right? You're like there's a lot more kind of non-determinism, or like maybe you have to like interleave. Yeah, right, yeah, exactly. You might be using a relation in multiple different modes or something. So how does that affect, I guess, there were some parts of what you were explaining that I wasn't really following, so maybe it's in that, but like, how does that affect like the way you have to write down the operational semantics?
If your operation, the primary operation is either substitution or the internal execution for unification stuff. So if you treat unification as atomic, then the assignment and back off stuff you then can get away with without needing to think about the order of operations. As far as substituting variables for values, or logic variables for lexical variables, or parameters in a relation for terms, then it's just plain substitution, and you can get by without needing to think of it in terms of the input or output.
Okay.
The terms themselves have logic variables still in them.
Got it. Okay, cool. Thank you.
So we've been bad historically at things like synthesis when we do small step because of this problem, which I call, the broken wires.
Yeah, the disconnected wires.
Disconnected wires where it's difficult to fail fast because you have to be able to prove that a certain state is inconsistent basically, or can't reach a consistent state. And it seems like when you're doing things small step that can be quite difficult. Whereas with some of the big step semantics or implementations that in some cases it's pretty obvious like how you show that some states are inconsistent. So I'm just curious if what you're showing helps with this issue, and also is it related at all to things like Knuth-Bendix completion? And also, did all the bookkeeping you added, did that help? Would that help with like back jumping or conflict-directed clause learning or things like that as optimizations or things like,
Cool. That's like fodder for like 3 questions.
Yeah.
So let me see what I got. Let me see what I retain. How would having a small step reduction semantic for the implementation help possibly have anything to say about the execution of this in miniKanren. That should obviously be, or any of our others. Can some of the like Michael's letrec trick, can you somehow inherit features from this that would be useful? I don't know. I have no idea how to think about that, but it sure would be cool to find out. I don't think that any of the stuff that we're tracking is. I don't think that any of the information I'm tracking about where things were crashing, where delays were forced, is going to be useful for that. But I don't have sounds possible, but I don't know that I've got any silver bullet on that. Swell. Other questions?
I could ask one more if we
I guess maybe one more and then we can.
Yeah. Okay. I have one more. This is more just like speculative. So something about the way you were kind of characterizing the like left and right, and I know this is not exactly what you were doing, but sort of labeling them was making me think about proof terms. So I really like to keep track of proof terms when doing at least certain kinds of logic programming where that's possible. Is that a thing you've thought about?
Only so. Frank Finning gave this really cool talk at Foundations of Programming something something at Flock a few weeks ago, and it was super duper neat. Cool. There was like not just here's our standard, well, what if we add modalities to it? Then what if we go to linear affine logic? And also, what's the Curry-Howard equivalence of compiling down to a lower level language? What does it mean to take programs, proofs in some high level language logic and turn them into in a lower level language logic? And I thought that was really neat, and I never considered that. And I kind of made me wonder what it would be like to what's the under the Curry-Howard-ish thing of doing this sequence. That's all I got on it, but it made me ponder.
Cool. I know a little bit about how Frank thinks, so I can, if you want to, I can tell you a little bit more after this. Yeah.
That's swell.
Let's thank our speaker.
Oh.
Thank you. Okay, the last session of the day. I think, Chris, you're on deck for this one. Chris gave us a challenge at the beginning of the day, and I think we'll get to see. I know there was at least one person other than Chris who's tried to implement it. Maybe we have a couple people. I've actually implemented a bunch of versions of this in the past as part of the PAIP book on.
So you're a ringer.
I'm a ringer, and I have to say I didn't even have 10 minutes to sit down and do it today, but I have a bunch of these, and maybe other people throughout the week, if you have versions of it, you can show them off or post them somewhere online. We'll take a look.
Yeah, so I think I've already got a mic, I think.
Okay.
Yeah, so at the very least, we can make Will show some examples, but I'm hoping we can get some other people to show off first. And my thought about this is there's a Discord Q&A session there should be one for this session. So if you're on the Discord, probably the easiest thing to do would be to just drop either like a link if you have a link, or just like put in your name and say, hey, I wanna show something.
Programming challenge to attendees?
Yes, programming challenge. Yeah. Well, that was the morning. I think I don't know if there's.
This is like the demo and open mic session.
Demo and open mic.
Yeah.
Yeah. So, I guess the other thing we could do is just like show of hands who's interested in showing something. Maybe it doesn't have to be very complete. I'd love to see what you come up with. Okay.
All right. Oh wow, four
okay.
people.
Okay, nice. So maybe we can just go from like back of the room to front and see what we get.
Okay,
How long do we
so
want
I
to
guess
give
the
people?
question is, do we want to try to hook up laptops
Yeah.
and all that? Is that okay? And the other thing is, I think we're streaming. Is that right? Are we streaming and recording or not?
We are, so if
Yeah.
are okay with that.
So yeah, just be aware that you will be recorded for posterity. So if that's not cool, then we can do it offline or another way. Okay. I was okay. So we have some things to sign here. That's the preference, but my understanding is as long as you know and you're willing to do it, then probably it's okay. All right, but be better to get your signature on it. Okay. So if you're willing to be recorded and YouTubed and all that, you can come on.
Sign on your behalf if I just know your name.
Yeah.
All right.
Okay.
So, and we do, I guess technically it's like 20 minutes left in the session. So let's try to be mindful of time. If we want to get through 4 people, that's like about 5 minutes per demo.
Okay. Well, we can put them on the clock.
All right. Sounds good. Can you keep track of time? Can I ask?
Okay.
that
I
from you?
will
Okay.
keep track of time.
Appreciate that.
Yeah. All right. So, first volunteer.
From the back of the room.
Yeah, it's going to go around this order.
All right. Got 5 minutes here.
It's probably, is it still on there? I stole your adapter.
Oh. Okay. The communal adapter. You don't know how many of these I've lost over the years. They've been communalized.
There's a reason I don't have mine anymore.
There's a reason I carry 2 or 3 at all times. And I don't even need one anymore.
I need to hold in my hand, or is it good?
And so when you do your demo, if you would introduce yourself, please, and then maybe give a little context as to what you're trying to solve. And
It's good. I'll need to change the projector settings. Why is it extending my display? Or if I just move the window to the secondary.
do you need, well, okay, there you go.
Yeah, I cannot do the mirroring, but anyway. Hi everyone. My name is Xiang Yu from Arizona State University. Here is my approach to solve this challenge in the miniKanren. So basically for the first one, I think we already provided the start and the end states from the input sentences, right? So the start states is just starting with the D. End states would be a bunch of fox, dogs, and cats. And all the transit can be learned from the input. So each word, like there's a lead after the end, the quick after the B, fox after brown, etc., etc. So once we come up with all this kind of the fact database, we represent the graph and all the edges. Now we can write relations to generate a sentence. So we will come with starting with the starting states. Starting state, if we have multiple states, we can unify with multiple starting symbols, and we just recursively traverse through the transition functions until we reach the end states. So for the recursion part, because we already picked one starting state, then use the accumulator style from the logic grouping part. So we're just constructing the sentence step by step. Then in the recursion part, we have two conditions. First one is that we reach the base case, and we can just stop. Now the accumulated sentence is part of the answers. Otherwise, we just keep transiting from this epsilon, keep going down to the next characters, and extending the accumulator and recursed. Then for the second one, I think we given a bunch of the types. So for example, the lead is a dog is the noun, adjective kind of things. So similarly, like we represent all these kind of type relations as the graph of the edges. Then we given the grammatic template. So this is a grammatic template I got from the challenge. Then similarly, we can have solutions to it, like we given the grammar template and the sentences. So we first would break down the grammar template using the console, taking the first one element and the remaining ones. And for the first one, we need to find out, okay, what kind of the words can be taken from based on the grammar template.
1 minute warning.
Okay.
1 minute.
Almost done. Yeah, then just recursive over it. So similarly for the recursion part, when the grammar template is depleted, run out, we found the answers. This is the accumulated. We unify with the output. Otherwise, we just grab the next element from the grammar template and the recursive of it. Then the last one is like, okay, now the starting states and the ending states change to the these two. So same representation. Okay, starting states we have the that, then stopping state we have noun and the adjective. So same mapping for the word type. Then now the transition function changes from for example, the adjective change to adjective change to noun. Also got from the composition document. Then lastly, similarly, we can have the solution to it. With starting from the starting state, we're picking out each word based on the type. Then we recursively traverse it until we reach the end state. So once we reach the end state, we find the answers. Otherwise, we just recursive for it. Thank you.
Thank you very much. Okay, if people are willing to post these and put links in the Discord, that'd be great to be able to review these. Thank you. Next volunteer.
Am I hearable?
I can hear you, but I'm standing right next to you.
Our AV people give you a thumbs up.
Okay, perfect. This is what we call a shameless plug for what I'm going to be presenting at Lobster. But what I'm going to be presenting at Lobster is a miniKanren, so hey, that worked. Most of this code is actually boring stuff of just reading through files that has that. I computed it. The important thing is that eventually we get a mapping of categories to word. Oh, bigger, sorry.
And can you introduce yourself, by the way?
Oh, hi, I'm Kyle. That's important. I'm Kyle Dewey. I am giving a talk on this library called Ren in Lobster.
Which is at the end of the week.
Yes. Yes, it's written in Scala. It was intentionally designed that this is portable to basically, or not basically everything, but anything that's eager, has garbage collection, and higher order functions and mutable state. If you got those things, you can port the library. Most of this code is just the boring parts of, like, here's different parts of speech for different words. The important thing is that we do have this mapping of categories to words. We have a mapping of this category. There is a transition from this category to these other categories have been seen, and then these categories are end states. For this particular library, it's based around iterators. This library can do unification, but I didn't need it for this. This library also has kind of a built-in state monad, so that state just holds all that information that's needed in there. The way to read this is that given a word or given a particular category that you're starting on at a particular bound, this also walks through all the possible sentences that are of a given or max given length. This takes the state and then it will generate a list of words, and it's will just iterate through different lists of words. So with respect to the bound, if we exceed the bound, we have no solutions, empty. Otherwise, grab the state. We need that state for some further processing. Emacs really wanted to mess with the formatting there. I kept fixing that, but it had other ideas. Take the current category that we're at, find a word for that category that goes into whatever the mapping a category to words. From there, non-deterministically, look to see if that category that we're at is an ending category. Then we can just say, yep, here's the end of the list. Otherwise, empty, and I'm realizing that that should probably be a list of cur word. My bad. Otherwise, another non-deterministic choice is look at the next possible category that we could see, extend the sentence recursively from that next category, subtracting the bound. And exactly how you walk through these with this library. So this does all the boring stuff to read in files and such. This does end up boiling down to an iterator-like construct. So from the start, extend the sentence from the start. Finally, at the end, actually take this list, turn it into a string, and then we just have a while loop that's walking through every possible string that gave us.
1 minute warning.
That is perfect because, just to show this, I was playing with this. This is able to generate all those. Sorry. Oh, sorry. Text is tiny. Fun fact, I normally look at text that small, and I do not have good vision. It doesn't make sense. But basically, it's able to generate all those, and I calculated the generation rate. If you ignore printing, it's about 1.4 million per second. Selling point of this language is, this library is it's fast. It's fast. Cool. Thank you.
All right, thank you, and check out the lobster talk. All right. Next volunteer, please, and please remember to introduce yourself. And I hope people will post code, and I hope people will play around with this. We've had, along with Chris's implementation, 3 implementations so far in 3 different languages, which I think is quite cool. The and relational programming part is coming into its own. That's right.
Oh, yeah. How about here? Like that? Will that work? Is that coming through okay? Like that? How's that? I think that's better. Is that good? Yeah. Okay, so he said I could do it. I'm going to do it. I never...
Who are
miss
you?
A chance. So I'm Aaron Sue. I do APL. So this is this is the solution. And actually, this isn't really the solution because only Big Markov, Gen, and Run are the solution. The other 2 are like helper utilities to have fun. So the basic idea here is we've got the text, tokenize. We'll let you tokenize the stuff. And what we can then do is we can generate, let's see, bigram Markov on text 2.
And so we will generate a basically a relational table, all of the matrices, with a symbol table indicating the unique words that exist inside of the table. And then we can, pretty print that. So we can look at what the table actually is saying, how it looks. And so then we can go from that, and we can actually walk through how this works. So if we step through this and go in here, the first thing that we do is we do some tokenization. So I will try to make this visible. These are you can see the left and right arguments that are being worked on. So we've got, and then that little red square, if you can see it, is where we're executing. So we're just doing a tokenization right now, and we tokenize all the words. Once we're done with the tokenization, we go through that, save it to a variable, and then we do a symbol table. So we generate a symbol table. So instead of working off of the strings, we turn them all into small integers so that we're no longer working in the domain of strings. We're working in the domain of numbers. So then our tokens are now integers. And then let's see if I can, we're going over here. We're going to generate the size of the table. So that's 14 by 14. We're going to generate our little matrix called our relation, which you can see over here. That contains nothing yet. Let me see. For some reason, it scrolls back every time. But the next thing that we're going to do is generate our bigrams. So I'm going to hide this one here. And that should give you guys enough to see it. Yes. So I'll close this one out. There we go. So that 2 there, we just sort of, we're going through and we're generating our bigrams. That's what the 2, / does. So the 2, / will go over our tokens, generate all the bigrams. We generate a matrix from that. And then from there, we compute a histogram. So let's see if we execute. Yeah. So this little guy here, the alpha tally omega, that's rectangle, that's computing our histogram of all the bigrams. So we get a count of all the different unique bigrams to work with. Then we convert that into a workable shape. And then we set every relation for every bigram to its appropriate weight. That's what that says. And then we compute the probability score instead. So previously we have a histogram. So then we do the RL divided by the sum of each column to get a floating point number from 0 to 1, or that adds up to 1 across all the numbers for our probabilities on the Markov chain. And in the 0 case, we just make sure that they stay zeros. That's what the 1 ceiling does. And that gives us our table of these pieces. And so to play with that, I couldn't help it. My daughter really likes Pride and Prejudice, so we grabbed Pride and Prejudice.
1 minute warning.
And we create Austin BM of bigram Markov, Austin Pride and Prejudice, and that computes that. And then what we can do is we have this generate, which goes through and generates a random word when we're given out of transition. And then our run function is going to work a little like the miniKanren run. So we're going to use Austin BM, and we're going to run and produce, say, a 30 size piece, and that produces our text of a given type according to Austin with the bigram probabilities. So, any questions?
2 questions. Technical question and a serious question.
Okay, we have 15 seconds.
15
So
Okay, serious question. Someone hands you that piece of code. Can you read it?
Easily. This is like bog standard trivial.
you're talking to the APL expert, of course.
I'm just doing nothing but chaining together idiomatic phrases that every APLer learns on like month 2 or 3.
Technical question. Is there a domain of symbols in APL so you don't have to go through numbers?
No, because it's slow. Just make your own symbol table. It's better.
Okay, thank you very much. Please post that. All right, did we have one last person? Can we squeeze them in quickly? Okay, come on up. And please remember to introduce yourself. And please remember after this, anyone who's interested will go out together and get some food or order food or something, and we can talk about miniKanren until relational programming until you go to the farm event, or we can just hang out and hack miniKanren all night or whatever, or APL, who knows. Okay. There we go. 5 minutes.
All right. So hi, I'm Andrew Chen. I work at Minnesota State University in Moorhead. And so I'm really impressed with the diversity of implementations. I thought this was the most straightforward one. So we were given some sentences, and I wanted to encode the parts of speech. I wanted to figure out the bigrams from those sentences. And I was going to do something with the bigrams, but I never got around to it because I got busy with the grammar stuff. So first, I figured, well, let's define what's something that's nounal. And so, is it a noun, or is it like a noun with an adjective or an article in front of it? Then, is it a verb, or is it a verb with an adjective in front of it? And then, well, maybe there's a prepositional phrase. And so, either it's a verbal that does or does not have a prepositional phrase after it, or it's a nounal that does or does not have a prepositional phrase after it. And then, of course, we have to have this definition of a prepositional phrase, and part of why we had to have those others first is because that might be that might have a nounal in there. So the noun in the prepositional phrase might have a prepositional phrase after that. And so I was like, okay, well, now that we've got this, we can now have a grammatically correct sentence. So we can have a noun and a verb, or maybe it's one of those sentences that has a noun, a verb, and an object. And so we have that defined. And so then it's just a matter of generating all the grammatically correct sentences, of which there's some odd things here, but here this run 5 is the one that will actually be relevant here. And so we can actually go ahead and run it. And, oh, I just changed something. It really did work. That comment was the one thing that I changed. There we go. Cool. So here we have the 5 implementations, the first 5 grammatically correct sentences. And so that's it for me.
All right. Thank you. Thank you. And if anyone else wants to post their solutions, please go ahead and post it to the Discord channel, or we can show it off to each other later in the week. Thank you very much for attending the 2026 miniKanren and Relational Programming Workshop. On behalf of myself and Chris, I'd like to thank the program committee, all the speakers, the attendees, the student volunteers. Thank you very much. And everyone who's attended and everyone who showed off their hacks today. Thank you, and hope you enjoy the rest of ICFP, and come to Lobster, see the talks, come to PPDP and all that. And so if you're interested in hanging out more, we have to leave here, but we will somehow acquire food and hang out. And just a reminder that there is the farm live performance at 7:30. And does anyone remember where that is or how close that venue is? Walker's Theater. Okay, so I think it's fairly close, but it's not in this building, okay? So just be aware of this in the theater. And I hear they have like 400 extra seats right now, so you don't need a special ticket to go. You're certainly invited. Okay? All right, thank you very much, everyone.